And as one of our first speakers, co-advisors at Pulse, for me to kick things off. So welcome to this year's Astronomy 99 Senior Thesis presentations. I'm sure you'll see our seniors have been working extremely hard all year on the research they're going to be presenting to us today. So the co-advisor for our first speaker, Grant Miners, was Paul Grimes, who's also here. And Paul has done, honestly, most of the laboratory work in coaching Grant through a very challenging instrumentation project. And so I applaud Grant for all of the hard work that he's put into the lab. It's been a real pleasure to work with him since last summer on what are extremely challenging measurements of optical properties of dielectric materials that go into some of the most sensitive microwave telescopes in the world. So with that, I'll turn it over to Grant.
Awesome.
Take it away.
Thank you, John. Yeah, so hi everybody, my name's Grant. I'm presenting my senior thesis, a little bit of what I've been up to the last year, and yeah.
Huge thanks, ditto, to John and Paul for the help this year. It's been awesome. Yeah, I been measuring optical properties of dielectrics at ambient and cryogenic temperatures for use in cosmic microwave background telescopes. So, what does that mean? I skipped a slide. All right, so first a little bit of background, because I think my mom is watching. The cosmic microwave background is a thermal energy signature signal from the Big Bang, and it's interesting to cosmologists and astronomers because it tells us about the early universe's contents and structure, and so it's something that we really want to learn a lot more about, and something that we want to take very accurate measurements of. There are a lot of telescopes that take measurements of the cosmic microwave background. A few here at Harvard Smithsonian are the Bicep Keck arrays and the CMB S4 small aperture telescopes. Now they're not located here; they're worked on in South Pole and Chile. But they are used for the CMB and sort of some of like the I guess test telescopes used for this thesis as like an idea of why we're working on this. An interesting thing about these telescopes is that the optics are cooled down to about 4 Kelvin, and the detectors are cooled down to 250 millikelvin. And the reason for this is you'll notice that the CMB has a thermal radiation that is consistent with the blackbody spectrum at 2.7 Kelvin. And so not only do cooled down detectors and optics help ensure sensitivity and precision in our measurements, but they also help limit the other signals that we might be receiving from other black bodies in the area that might overpower that CMB signal. Right here we've got a cross-section of the CMB S4 telescope. And with all the optics listed. There are about 3 things we should note here. The first is that there's a vacuum window on the top. So because of the way that these telescopes are cooled down, they need to be maintained within a vacuum in order to maintain the low temperatures. And so the vacuum window is one of the most important parts of the telescope because it maintains the vacuum as well as is the primary aperture for all of the signal that we receive from the CMB. Other things to note are the various filters and lenses, and it's important to note that this is a refractive telescope, not reflective. So those filters and lenses not only help figure out what light we want to receive, but they also help direct the light towards the actual detectors and create the image that we want to see. And finally, on the left, you'll see the temperatures at which all these optics sit. As you can see, there's a range from 100 millikelvin to the ambient temperature around 300 Kelvin. And that's sort of the crux of the problem here, is that we don't totally understand all the optical properties of these materials at the various temperatures that they operate at. We have good guesses, and there's some past literature that has estimates, and it's been working fine so far, but we would like to get as accurate as numbers as we can in order to make sure that we're making the right judgments when we create these optics and create the recipes for them. So that's the motivation for this project. We want to make telescope lenses that are minimally lossy and minimally reflective so that we're getting as much signal as possible, as well as I mentioned, they're refractive. It's a refractive telescope, so knowing optical properties such as the index of refraction and the loss tangent are very important in making sure that we're directing the image towards the detectors in the correct way. And then obviously the loss tangent helps us make sure that we're not losing too much signal as it goes through the telescope. We want to make a data set of the optical properties for CMB optics and materials of both ambient and cryogenic temperatures. That was the ultimate goal of this thesis. How are we going to do it? Here's our method. Sort of 3 steps. The first is deciding what method to use. For this, we decided to use a Fabry-Perot open resonator technique with a VNA, and I'll explain all these in a little bit. And then the second method was to develop the Python code that would actually interface with the VNA, collect our measurements, take the data, and then analyze it and output numbers that are actually usable at the end of the day. And then finally, in order to accomplish the cryogenic measurements component, which is obviously the ultimate goal of this project, we decided to design and construct a new test cryostat for making those measurements at cryogenic temperatures. And I will go through all three of these sort of methodologies. So first, just a little bit of background on the VNA. Broad strokes is just that the VNA is an instrument that can generate and receive millimeter and microwave wavelengths of light. And we use that because those are the frequencies at which the CMB emits at. And it outputs data in the form of reflection and transmission measurements. So you can just sort of broadly look at this as like, this is the sample that we're looking at, the cavity eventually that we'll be looking at, which is sort of our circuit. And the VNA will send in a signal. The signal will go through the cavity, it will be transmitted outwards, and it will compare the outcoming sample with the incoming to get the transmission measurement. So yeah, broad strokes is just that the VNA is the instrument we use to generate the signals. As part of the Fabry-Perot open resonator technique, you need an open resonator cavity. So what we have here is the quasi-optical resonator cavity theory. So this is a cavity. This is just sort of a picture here, but you'll see a picture of the real cavity in a few slides. This graphic shows the cavity as it works. So there's a spherical mirror on top of the cavity and a plane mirror on the bottom. And the way it works is you'll see two apertures on the top. One inputs the signal, and then it bounces in through the cavity, reflects back and forth, and then it goes out and outputs through the other signal every time a measurement is made. And then that's how the incoming and outcoming signals are measured in order to make transmission measurements. And then you see we can put a sample in here, and the reason, okay, well, first I'll explain the fact that the cavity has resonant frequencies that are described by the length of the cavity and the radius of the spherical mirror up there. They're described by this equation, which I'll explain in a second. But basically the important thing is the cavity's dimensions determine what resonances we expect to see. And also, when we put in a sample into the cavity, that changes the resonances, not only in frequency, but also in shape. And we use those changes in frequency and shape to actually later determine the index of refraction and loss tangents of the samples themselves. We expect this method to measure low loss very easily and index accurately compared to reflectivity and radiometric measurements. And the reasoning for this is because you can imagine that when we send in a signal in here, it's going to reflect back and forth many times. And so each time it reflects, we're sort of pinging and measuring those values. Whereas with the radiometric or reflectivity measurement, it only really goes through the sample once. And so it's just maybe a more accurate method of measuring. We expect this method to be limited by the accuracy of the measurements of the thickness of the sample, which is another important component. This is primarily because it's something that we just sort of measure ourselves, and it's not going to be consistent across every sample. It's going to be close, but it all depends on how it was machined. And so that's sort of where we expect most of our error to come about. And yeah, so here I'll explain a little bit about the frequency equation. So you'll notice that we have sort of three things here that aren't really defined, Q, P, and L. Those are the index mode numbers, or sorry, the integer mode numbers that describe what mode we're working with the cavity in. So Q is just an axial mode number, so it simply describes like the number of wavelengths that the cavity, the length of the cavity in a number of wavelengths. And yeah, but the P and L are Gauss-Laguerre modes, as shown on the picture on the left, and so they sort of describe sort of more side-to-side changes in phase. And yeah, for this project, we're basically only looking at the fundamental modes. There's a bit more math involved in making sure that we can line up the higher order modes to indices of refraction and loss tangents, and we haven't really gotten there yet. So we're primarily just looking at Q equals N modes for this project, something to think about. And so that's to say that every time we measure the sample, it is just a Gaussian beam that we're measuring, or just a Gaussian, I should say. Okay, and here's a picture of the cavity as it is in the lab compared to the graphic. You can see over here we have a spherical mirror on the top of the cavity, and on the bottom is just a plane mirror. That's what allows the resonance or signal to reflect between the two. Here you'll see this is connected to the VNA, so the signal is input here, it bounces around, and then it comes out and goes back to the VNA there. Another important, interesting thing is here is an actual sample. So this is typically what our samples look like. This is maybe 2 or 3 inches by 2 or 3 inches. And yeah, this was probably like 1 millimeter HDPE or something like that. And so that's what the samples look like when they're in there. Nowadays, we've been clamping them down to make sure that the samples are staying flat. But yeah, this is an early picture, just to get a visual of what the cavity looks like. So how do we actually take the measurements? So this is an output of from the VNA of a measurement of an empty cavity. So that is a cavity with nothing in it, simply based on the fundamental resonant frequency equation. You see on the bottom, frequencies we're looking at are 75 gigahertz to 110 gigahertz. That's simply because with different types of waveguides, they can only accommodate certain ranges of frequencies. And for this one, we used one type. And on the left, you'll see that this is a measurement in magnitude in decibels. So you'll see that we do get resonances that are pretty pronounced and very clearly there. So the first step is we have a lot of resonances, but we know that some of them are higher order modes, and as I said, we're only really focused on the fundamental for this project. So we need to identify which ones are fundamental and associate them with certain Q values, that little Q that I showed earlier, so that we can make sure that when we have a loaded cavity that has a sample in it, we can associate the same resonances with each other and not compare two different Q values. So we use the equation that I showed earlier with the Q, P, and L, with P and L set to 0, and then we find the resonances that we expect in this cavity. And so you'll see here on the blue is what that equation outputs as the expected resonance, and the red is what our SciPy peak finding algorithm finds as the closest actual peak. So it works pretty well, but we do expect there to be a bit of a difference, and this difference comes about because we don't expect the cavity length and the spherical mirror radius to be exactly what we mechanically ask them to be. We expect them to change a little bit via thermal contraction or just the mechanical tolerances that we had to work with. So because of that, we want to then measure derive the cavity length and spherical mirror radius from the frequencies that we actually measured, because then we can actually get more accurate numbers of the radius and length that we can use for later equations. So we use this exact same equation that I showed earlier. We input the frequencies that we get, and we use a SciPy minimizer function to retrieve the cavity length and the cavity radius with just our priors being what we asked them to be when we had it mechanically created. And so once we have those, we can move on to a loaded cavity measurement. A loaded cavity measurement is just a cavity that has a sample put inside of it. And so you'll see here in sort of like the tan orangish color, you'll see the empty cavity measurement, and then the gray color shows the loaded cavity measurement. And so you can see here that there's very clearly a frequency shift when a sample is put in. Maybe the best way to look at it is right here. You'll see a sort of double peak, and then right here you'll see another double peak in between the empty and the loaded cavities. And so you can see that it's shifted by about 3 gigahertz or so. And so we want to mark this shift to find the index of refraction and the thickness of the sample, and so we also want to make sure that we're comparing the same frequencies to each other. We don't want it to be the case where, say, it's actually shifted over here, but we're comparing this one and this one. So we want to make sure that we assign the right Q values to each of these as well. So in order to do that, we go to a field matching calculation. This matches the fields between the empty cavity and the sample itself at the boundary. We use a similar minimizer function with sort of our assumed values of index of refraction and thickness. The thickness value we get from our own measurements, the index of refraction we get from previous literature. And as I said, these have worked pretty well in the past, so we expect them to be pretty close. And we input those and we get back out the wave number and we convert that to frequency, and then that's how we get the frequencies that we expect to find in a loaded cavity. So doing all that, we then get here, and you'll see there are blue and red X's here, and they're basically in the same spot because it works pretty well at identifying the frequencies, and the SciPy peak finding algorithm then finds the closest frequency, and it's worked pretty well. And so that's what we use to find the resonant frequencies inside of a loaded cavity. So once we found that, we can then go back to this transcendental equation, and then we can actually try to figure out an index of refraction and thickness based on our own measurements. We go back to this equation, and instead of solving for wave number this time, we input the frequencies that we measure, and we take out the index of refraction and the thickness based on some of the priors that we give it, about a 3% accuracy in the literature values, and for the thickness, our own measurements of standard deviation. And another thing that we can do at this stage, this is a bit experimental, but we can try to do MC-MC fitting. So right here you'll see some walkers. And just to explain this a little bit for those who don't know, what we do is we sort of give it a range of thickness values to start, just based on a normal distribution, and then a range of n values just sort of uniformly distributed. And then we allow them to walk along a bunch of steps in order to try to minimize themselves. And then this allows us to get a range of values for index of refraction and thickness at the end of the day. And this will actually allow us to put errors on our estimates because this system is super degenerate. I mean, there's so much stuff going on and there's a lot of values at play. And so there's a lot of combinations of N and T that can get us the fits that we expect. This is still a bit experimental. This is probably the best representation of the one we've done so far. So we don't actually use this yet, and these next results I'm going to show don't have it, but it's something that I think we're working on and hopefully can be implemented. So here are some examples of some of the results that we're looking at. A few things to explain. So for the samples, the first 6 that you see here, the 3L window samples, they are all the same recipe, just the mirrored ones are flipped. And so we expect them all to have the exact same index of refraction. Obviously, that's not the case. This is the index of refraction that we find. This is the one that we assumed. We assumed it was around 1.55. This is what we looked for. We have a good amount of them that are about 1.54, so that might be promising, but we also have some others that are just kind of off. And there's still a lot of inconsistency here and some systematics that need to be worked out, but these are initial results, and it's promising that we're at least getting within the ballpark that we expect. This HDPE that you'll see on the bottom is probably a little bit less accurate because we don't actually have measurements of the thicknesses of those, or at least not an idea of the errors on those thicknesses. And so take it with a grain of salt, but as I said earlier, the thicknesses are going to be our biggest estimate, our biggest introductions of error into the system. So that's to be expected, I guess. But the process works, and so we're happy about that. Okay, the next step is to measure the quality factors or shape of the cavity. A quality factor is sort of the energy stored within the cavity divided by the energy lost per cycle. And it's a measurement of the shape of the cavity. And we expect the quality factor to decrease between a loaded cavity and an empty cavity because when you load in a sample, you're going to introduce more loss, and part of this shape is determined by the height of the actual resonance, and so more loss, you're going to have less height because less intensity. Less is actually transmitted. So on the left, you're going to see empty measurements. On the right, you're going to see transmitted measurements, and there's a few deviations in shape and obviously a lot of noise, but we can quantify that shape with Q factors. So Q factors are defined loosely as the frequency over the full width at half max. So that's a little bit about why with a loaded cavity you expect less smaller Q factors between the empty and loaded cavity. Here are some comparisons of side-by-side measurements of frequencies between the two. So you can see that they do decrease when a sample is loaded. The gray ones are loaded. And so here's a little bit about how we've been measuring the Q factor with the full width at half max. The red X indicates the central or maximum frequency, so that's the resonant frequency we're looking at. The green and blue are respectively the left and right sides of the full width at half max. But this method is not completely accurate because, as some of you might have noticed, these are not ideal resonances. This is asymmetric. So we need to go a little bit further. The Lorentz model is ideal, but we can use the Fano model, which is a non-ideal model of resonances like this. And it introduces a complex cross-coupling term, which then allows us to actually fit to these asymmetries and solve for a closer Q factor than what we're getting with the full width at half max method. We use the full width at half max method still to get like an initial Q value or Q factor that we expect to be close, but this is ultimately what gets us a better Q factor. And so you'll see here, the blue is what we would expect with an ideal Lorentzian resonance, while the red is what we actually fit to with that cross-coupling complex term. And you can see that the red obviously does a lot better, and so the Q factors that we're getting out are a lot closer to what actually are the Q factors. Here you'll see that the empty Q factors, which are the red ones, are higher than their paired loaded Q factors. So for example, like these two are in the same pair, this one's higher, and that's what we expect to see. Okay, finally, we can now calculate the loss of our sample, tan delta. So these are all the equations involved. There's actually a few more that aren't listed on this slide, but there's a lot of things that need to be defined. But the basic point to be made with this slide is that To calculate the loss tangent, we use the spherical mirror radius of the cavity length, the index of refraction, the thickness of the sample, and the loaded and empty quality factors. So everything we've measured up until this point comes into this final equation to get out a tan delta. So obviously, any errors that we made previously can also propagate through. Here are some of the results that we've gotten for the exact same samples I showed earlier for the index and thickness measurements. You can see that some of them are pretty off, but some of them are closer to what we expect. Again, the first 6 we expect to be the same. They're not. But they are within an order of where we expect them to be based on radiometric measurements that were taken at South Pole. For the HDPE samples, again, take them with a grain of salt because there were thickness issues. But you can see that like within the literature values that we can find, this is all from Lamb, it ranges by quite a bit, and that's why we want to constrain these values. Okay, finally, just a really brief, because I know I'm at 20 minutes, introduction to the cryogenic side of things. The third part of this process was to actually make a cryostat that would actually measure things at cryogenic temperatures. There were 3 goals. Cryostat. What is a cryostat? Cryostat is something that is cooled down to cryogenic temperatures to make measurements. This is what the cryostat looked like about a month and a half ago as we were constructing it. There were basically 3 things that we cared about with the cryostat. We wanted to make sure that it could contain the quasi-optical cavity and make measurements and have enough room for all the instruments involved. But we also wanted to make sure it could maintain a vacuum because, as I said earlier, to get to those low temperatures, we need a vacuum. And finally, it needed to cool down a sample to around 4 Kelvin. There are 4 components. I'll run through these briefly. The first one is the vacuum shell. This is the interface between the outside world and the inside of the cryostat. Took a lot of design work, and it maintains a vacuum, basically. O-rings, something that we had to think about to make sure that there was a good seal between the surfaces enclosing the vacuum. The next part of it is the radiation shield, which you can see came in many parts. But the radiation shield's purpose was to limit the ambient temperature from reaching the inner cavity. So you can imagine that this is exposed to the outside world. The vacuum shell itself is probably sitting around 300 Kelvin. But we want this to be cooled down to 4 Kelvin. We can take out a vacuum, but there's still going to be a thermal radiation from the vacuum shell to this inner cold plate that we want to cool down to 4 Kelvin. So we introduce a radiation shield, which connects to our cryocooler and is sitting at 50 Kelvin. And this is sort of where you get sigma T to the 4th. We can reduce the temperature heat flux into the cold plate by introducing this radiation shield. And based on my calculations, it's roughly like a factor of 1,000 reduction in heat transfer. So it's a very useful thing to include. And it just sort of sits between these two to block out the heat transfer. Cold plate. Important thing to note here is the 4K cold stage is just from an off-the-shelf part. It's a Cryomic PT405 cryocooler, and it transfers the heat here. Everything you'll see here is copper, the heat straps, the cold plate, the cold stage, because obviously copper has a very good thermal conductivity. And this is how we actually cool down the sample to the 4 Kelvin temperature that we want. Heat straps, cryocooler, it's got 2 stages, 50K and 4K, connects to the radiation shield and the cold plate. I just thought this was a cool picture to sort of like build up the cryostat in a sense. So over here, you'll see the cryocooler itself, and the 4K plate is connected to the 4K stage is connected to the cold plate. Then we add the radiation shield, which is at 50K from this stage. And then finally, we add on the vacuum, and it works pretty well. We've been able to maintain a vacuum of 10 to the minus 5 millibars, which is roughly 10 to the negative 10 atmospheres, and we've also got the cold plate down to 6 Kelvin. Next steps are to do some more integration of the actual components, electronics, and waveguides and stuff so we can make measurements, and the cavity eventually. Future work, there's a lot to be done here. A few things to note. The MCMC fitting that I brought up earlier, still a bit experimental, but once we get that, we can get accurate error measurements, and that'll be really helpful. We need equations for the higher order modes. We're actually pretty much there. Paul's been working on it a lot. But that's something that can help us constrain our values a bit more. And then finally, we actually noticed like 2 days ago that some of the past literature equations were off by a little bit. And so there are small inconsistencies there. But it's something that needs to be implemented as well. Future work in the design, there's a lot that can be done here too. Obviously, full integration of the quasi-optical cavity into the cryostat as necessary, but also we can reduce leakage, and we can figure out ways to make those resonances more pronounced. This cavity was designed with an idea that Q factors would be about 100,000. We're getting more like 15 to 20,000. If they're 100,000, we can measure tan delta down to 10 to the minus 5, which is pretty accurate, but we're not there yet. So with more physical improvements, we can be there. Okay, so in summary, 3 things. The quasi-optical cavity technique shows promising numbers. I won't say that they're completely accurate, but there's still some work that needs to be done on the systematics and consistency of them. I'll say this. And the analysis program works pretty well. It's almost self-functioning at this point. There's like one stage where I need to look at it and make sure it's doing the right thing. And then finally, the cryostat is working well, and I'm very happy with where it's at. And I have some acknowledgments and a lot of names, but that's it. Thank you.
Thank you, Grant, for gracefully handling the video cut at exactly 25 minutes. We've got a few minutes for questions.
With the loss tangent measurements, is it good or bad that they're different than what you expected, or like how would they? Or at least also all different.
So for the for the 3-layer window measurements that we saw, between the samples, we would expect, I believe, the loss to be basically the same because the thickness of the sample is accounted for in the equations, and so what we want is them to be consistent, so that the number we put out at the end of the day is the same. We don't expect, we don't necessarily care if it was the same as the expected value. Obviously, the radiometric, I'm not discounting the radiometric measurement as inaccurate, but I mean, if it was different, that would just mean that there are 2 different methods of measuring something, and it could have been that mine was right or the other one was right. So yeah, probably the other one, but yeah, we want them to be the same.
Yeah, so I just wasn't clear. The material you're measuring, is that to make a decision about what to build, what to actually use, or are you actually using that material and now you're just trying to characterize it after that decision's been made?
Right, yeah. So the 3-layer window that I showed earlier, just to sort of go through some of the materials, there were a few more materials that were measured, but the process has been like changing like every day a little bit. So this is just the most recent ones. But for example, this HDPE, high-density polyethylene, is just a plastic that we use a lot in materials. So this is something that we're trying to characterize just on its own before being used. The 3-layer window is something that's actually like on a telescope right now.
Yeah.
So that's yeah. So that's something we're trying to characterize after it's already been made. Yeah.
That's right. So that the CMBS solar telescopes haven't been built yet, so we're still material selection. So it's feeding into the next generation of telescopes.
It's a $600 million project that's going to be relying on data like you started to generate to decide which kind of plastic is best.
Yeah.
So, absolutely. Charles.
So can you say a little bit more about the samples? Are they standard engineering materials, or are they highly processed design materials?
Miranda? Miranda's been the one handing off samples to me.
Yeah, so the HDPE is machined at one of the scientific machine shops. The windows are made by me, and therefore are potentially not as precision machined as some of the HDPEs. They also, just the processing of them means that their thicknesses are potentially a little bit more variable than something that is precision machined.
Yeah, the actual raw materials for the windows is a stack of commercial materials and Miranda's laminated up in the lab, so the actual bulk properties are bulk properties that's been made in the
Yeah.
The HDPE is a particular grade of material from a particular supplier. We use it for lenses. There's variation between materials and different suppliers.
Okay. Any other questions for Grant before we wrap up?
I have a question.
Sure.
So the device that was kind of gold-looking that you used.
The cavity?
Yeah.
Yeah.
Is that something that the lab has built in-house, or is that something you can purchase? Is that something that you played a role in?
So
I'm just curious to know what your connection was to this thing.
I did not design this. I designed the cryostat
Yes,
that you
no,
saw
I get
the
that,
SolidWorks
yeah.
stuff, but this arrived last summer as I was still interning. Paul designed it. But yeah, I
So
believe
it's a custom.
I believe custom from England somewhere. Somebody out there, Paul knew, who knows how to make these things. Yeah, it's all custom designed.
Great. Okay.
There's a few suppliers of these that mostly aim more at the microwave. They're used for measuring dielectrics using circuit boards, microwave circuits, but not really studying higher frequencies.
And what's the scale here? Like, what's the length of the cube?
This
Like a
is,
geologist would put a penny down.
this is supposed to be about 10 centimeters.
Okay,
I think.
great. That's awesome.
Yeah.
Thank you. So it's okay.
Or no, sorry, 5.5 centimeters.
Okay, so like that.
2 inches for us old people. All right, well, so there are no last questions for Grant. Thank you very much for keeping us on time.
Thank
Let's
you, guys.
thank him one last time.
We get it. You sure? Yeah. I'll wait until all right.
All right. So I've been very fortunate this year to work with 3 excellent senior thesis students. So you'll be hearing from the other 2 later in the afternoon. But we were all working together on new data that's come from the James Webb Space Telescope. So I think a common theme of these 3 projects is they were really all at the bleeding edge of trying to get data from James Webb to actually make sense and to to take advantage of the marvelous opportunities that the telescope is giving us. All 3 of these benefit a lot from help from Ben Johnson as co-advising. And so I'll start by introducing Maya Skarbinski, who has been working on utilizing the opportunities in this data with ultra-deep JWST imaging in the Hubble ultra-deep field, which has all the ultra-deep spectroscopy, and you're beginning to get the theme of why this was a good thing to do. But we really wanted to start with the basics of like, okay, what do galaxies actually look like in terms of their spectra? And so Maya's been doing an excellent job putting that together. It's Maya.
Great, thank you. So my name is Maya Skarbinski, and this year for my senior thesis, I've been working on producing a JWST SED library with my advisors Daniel Eisenstein and Ben Johnson. So studying galaxies at different redshifts is critical to understanding how galaxies evolve through cosmic time. The physical properties of the stellar populations of these galaxies can be interpreted from photometric and spectroscopic observations, and that can provide insight into galaxy evolution. And the new observations from JWST provide an opportunity to study these galaxies at a wider range of redshifts than was previously possible. So one way to study galaxies is by looking at their SEDs, or spectral energy distributions. Spectral energy distributions are plots that show the flux density versus the wavelength of light. So here's one example of an SED. The red points are showing the photometric observations taken at different filters, and then the gray lines show the inferred spectrum using those observations. So SED fitting can be used to determine the properties of these galaxies by matching physical models to these observations. And galaxies are composed of many different components, such as stars, dust, gas, and each of these components leave a distinct and different imprint on the SED. So for example, younger stars emit more in the UV or bluer part of the spectrum, and older stars emit more light in the redder part of the spectrum. Additionally, observational cosmology relies on accurately knowing the redshift of galaxies, but spectroscopic redshifts are available for relatively few galaxies. So SED fitting can be used to determine the photometric redshifts of galaxies, which is sort of like the next best option. So once you have all these observations, you can infer what the spectrum of an SED of a galaxy may look like. So one feature that's of particular interest is the 4,000 angstrom break. So you see a clear decrease in flux below about 4,000 angstroms. This is due to absorption features from metals in stellar atmospheres at wavelengths bluer than 4,000 angstroms. And the amplitude of this break can be used as an indicator of the age of a galaxy. So galaxies with a stronger break are going to be older. So now I'm going to talk a little bit about what past SED libraries exist. So the current state-of-the-art library is the Brown et al. 2014 library. This library has 129 galaxies, but it has galaxies with redshifts limited to redshifts less than 0.05. And high redshift galaxies have been found to have different properties, such as having different metallicities or different star formation histories. So therefore, these SED templates that were derived at low redshifts may not be as useful when they're being applied to higher redshift galaxies. Basically, with all of these new observations from JWST, we're suddenly seeing this very old galaxies at these wide range of redshifts, and we can't necessarily say that the galaxies we studied very well at low redshift are the same as these very distant high redshift galaxies. So this is where my project comes in. I'm trying to create an SED library across a very wide range of redshifts, utilizing the new JWST observations. So my library consists of 399 galaxies. All of the galaxies in this library have known spectroscopic redshifts between 0.1 and 11. This library includes 12 deep bands of near-cam imaging in the Good South region. I'll explain that in a moment. And these all cover infrared wavelengths. And basically, this library is going to be a really useful reference for higher redshift galaxies. So you can sort of use this SED library as a reference set when you're looking at higher redshift objects. So for example, you may be able to use this library to help improve determining photometric redshifts. So all of the galaxies in my sample come from the Hubble Ultra Deep Field or Good South region, which is the best place on the sky for multiband imaging. It's a very dark region. There's many existing observations in this field. So for example, there's many deep bands from Hubble. But now there's 14 new bands from JWST, which I was using for my project. So I was using observations from two programs, JADES and GEMS. And the space-race resolution from JWST will really allow for crisp and accurate measurements of the photometry of these galaxies. So I had there's been a lot of time spent on spectroscopic observations in this field over the past 20 years, so there actually is a lot of spectroscopy in this area. I was using 3 data sets. The first was MUSE, which is located on BLT in Chile, which gave a lot of redshifts between 0 to 3, 0 to 5. And then I was using Fresco, which is a program that was using JWST slitless spectroscopy. And then finally, I was using near-spec observations from the JADES program. So here is where all of my galaxies fall in RA deck space. So for the 3 different data sets with different varying redshifts, here's where they fall. And then in terms of the actual redshift distribution of my final library, I have a lot of redshifts, galaxies with redshift from 0 to 3, 0 to 5, but I still have about 100 galaxies with redshifts greater than 5. So it's also very exciting because JWST was able to capture really good photometry of very faint sources. So my library includes very, very faint galaxies. So here I'm showing the flux in the F150 band, so 1.5 microns versus redshift. And just for reference, 100 nanojansky, so right about here, corresponds to an AB magnitude of 26.4. So over half of my sample is actually fainter than an AB magnitude of 26.4. So now we're talking a little bit about the imaging. I was using 12 near-cam filters. Here are 4 of the filters I was using. And these filters cover infrared wavelengths, which means that for high redshift galaxies, they're actually covering the rest frame optical, which make them really good filters to study for understanding the stellar populations of galaxies. And then to determine the photometry of my target galaxies, I was using the ForceFo code. So the ForceFo code will infer the fluxes and shapes of our target galaxies. Basically, it will fit every single exposure of every galaxy in every band that was observed in to some sort of model. That's going to be a superposition of Cirsic profiles convolved with the PSF, and that will generate a Markov chain of such models. So Cirsic profiles are basically just varying, looking at how the flux varies with the radius from the center of the galaxy. So here is one example of a force flow output. Here we're seeing the actual data in several different exposures. So this is for one galaxy in my sample. And here's the force flow model. And here I'm showing the residuals, so the difference between the data and the model. So we can see here that in this one, there's still some sort of residuals remaining. So the force flow model didn't completely capture the data. So there's still some bright central region in the galaxy. So what I did is I went through by eye and looked at all of the force flow models and identified cases where the force flow process could be improved. So in this case, I found that adding an extra peak to capture that bright central region would better improve the model. So here I have multiple peaks to better capture the flux of the galaxy, and we can see that the residuals are improved. So there's a lot of different things you can do with this library. One thing that you can do is use some sort of SED fitting code to interpret the stellar populations of the galaxies. So I used one SED fitting code called Prospector to infer these stellar populations. And Prospector was able to produce a most likely spectrum given my photometric observations. So here in blue, I'm showing the photometric observations from JWST, and in green, I'm showing the best fit spectrum to those observations, and in orange, I'm showing predicted photometry given this Prospector fit for the spectrum. So now I'm actually going to show some of the SEDs. There's 399, so I'm only going to show a couple. But here's the image of a galaxy at a redshift of 0.2, and there's this SED. So the first thing that we can see is that there are horizontal error bars that corresponds to the width of the filters. There are also errors on the fluxes, but the flux errors are so small, they're actually smaller than the point itself, so you can't see them. To get a sense for how faint these objects are, there's a dashed black line, which corresponds to where an object at an AB magnitude of 25 would be. There's also a yellow and red line that show where the H alpha and O3 lines are. So here is an example of a galaxy at a redshift of 3.3. Again, we see by the black line where an object at a magnitude of 25 would be. And we can see sort of elevated fluxes where the H alpha and O3 lines occur. And then the third SED I'm going to show is the SED for a galaxy at a redshift of 7. So this is a very, very faint object. That black line corresponds to where an object with a magnitude of 27 would be. We can see an elevated flux where the H alpha line occurs. And what's also interesting is that we see almost no flux in the FO90 filter or the 0.9 micron filter. And that's a common feature that's used to select these redshift 7 galaxies. So I wanted to see what happened, or what the general trends of all of these SEDs looked like. So I normalized and stacked all of the SEDs on top of each other. And interestingly, we see that the SEDs follow a pretty consistent trend over here. And then we see evidence of elevated fluxes corresponding to where the H alpha and O3 lines occur. At the lower end, lower wavelengths, we see much more scatter, but that's because we're getting into the UV range, and younger stars are more likely to be affected by dust, so we expect a little bit more scatter in that area. So next, I produced a UVJ diagram of these galaxies. So this is basically a color plot. And I was using Prospector to infer what these colors would look like. So this diagram is very useful for separating quiescent and star-forming galaxies. So galaxies falling in that top left quadrant are generally considered quiescent galaxies, and outside are star-forming. So from this plot, we can see that most of the galaxies in my sample are star-forming galaxies. This diagram is also useful for better understanding galaxy evolution. So galaxies falling sort of in this lower region right here or right here have been used to, that area has been used to select rapidly quenched galaxies. The fraction of rapidly quenched galaxies will increase rapidly at redshifts greater than 1. And for redshifts greater than 3, the universe was like less than a few billion years old. So if a galaxy is quiescent, then it must have quenched very rapidly, just due to the age of the universe being so young. So we may have some rapidly quenched galaxies in this sample, and we have a lot of star-forming galaxies in this sample. So next, I was looking at D4000. So that is basically the amplitude of the discontinuity for the 4,000 angstrom break over there on the left. So basically, D4000 is the ratio of the average flux density on either side of this break. And this is an age-sensitive feature, so that means higher values of D4000 will correspond to older galaxies. I selected the range of the wavelengths to exclude very strong emission lines, so this is really a continuum property. So here I'm comparing D4000 versus the specific star formation rate, and we can see that these two are clearly anti-correlated. And this is consistent with trends that we see in the literature. So next, I was looking at a galaxy that has a high specific star formation and a low D4000, so sort of in the upper left region. And on the left, I'm showing in green the best fit spectrum from Prospector. On the right here, I'm just zooming in around 4,000 angstroms. These two blue bands show the actual wavelength region I was using to determine what D4000 would be. And then these red lines show the width of the filters for the photometry. So this has a very low D4000, indicating that this is a very young galaxy. And we do see very clear nebular emission here, and we see very strong emission lines, which is consistent with a very young galaxy. So next, I'm looking at a galaxy that has a low specific star formation rate, but a high D4000, so it's an older galaxy. And we can see that this spectrum is sort of characteristic of what you might expect for an older stellar population, sort of similar to what you might expect for like a G-type star. So the last thing I wanted to look at was how Lyman break galaxy candidates are selected and whether these selections may be including low redshift galaxies. So the Lyman break, you can see right here, basically there's a super strong drop in flux below about 1,200 angstroms. So basically you'd see almost no flux in that lowest filter for us, like the FO90 filter, 0.9 microns, but you'd see a lot of flux. So that's a common technique that's used to select Lyman break galaxies. However, there is some concern that a low redshift galaxy with a really strong Balmer break right here could be misidentified as a Lyman break galaxy. So here's an example from a paper that was looking at methods for selecting Lyman break galaxies, these redshift 7 galaxies. And it finds that using this color plot, galaxies in this region are likely to be Lyman break galaxies. So I'm trying to investigate whether there are any galaxies that will have just a really strong Balmer break and be at a lower redshift and will be identified as Lyman break galaxies. So what I did is I took the galaxies in my sample that are between a redshift of 1 to 3, so relatively low redshift, and then I shifted them to a variety of redshifts between 0.8 and 2, and then using Prospector, I would predict what their colors would look like. So here I'm showing the same color plot that I was showing on the previous slide. So galaxies in that top left region would be where you would select for Lyman break galaxy candidates. So there are a few galaxies in that region, which indicates that there will be some contamination using that selection method, but it'll be relatively low. So there will be relatively few very low redshift galaxies falling in that region. So next, I was trying to figure out what redshifts this would most likely to happen at. So here I'm looking at several different redshift bins, and then for each line, I'm looking at one galaxy as it's shifted over a variety of redshifts, how its color would change. And we see that the colors tend to peak around a redshift of 1.5. So that indicates that redshift 1.5 galaxies are most likely to be falling into that selection method versus being selected for Lyman break galaxies. So in conclusion, I have a library of 399 galaxy SEDs with redshifts between 0.1 and 11.7. They all have known spectroscopic redshifts. This means that this is not necessarily a representative sample of galaxies. Galaxies that have spectroscopic redshifts are often brighter, but especially at lower redshifts, I probably do have a pretty solid sample. It's more at the higher redshifts where you may see those incompleteness effects. This library includes 12 deep bands of near-cam imaging in the good south region. It covers infrared wavelengths, which is really good for studying the rest frame optical for these high redshift galaxies. Also, the sample is really remarkable because I have so many faint objects, and the photometry from JWST is so good that I have very low error bars. I looked at all of the SEDs stacked on top of each other and found that they follow a very consistent trend with evidence of elevated fluxes corresponding to known emission lines. And then there's a lot of different things you can do with this library. One thing you can do is use SED fitting codes such as Prospector, which I use to do interpretations of the stellar populations of these SEDs. And then the last thing I looked at was whether Lyman break galaxies could be, how you select for Lyman break galaxies, and found that there will be some low redshift galaxies using the current selection methods. I have so many people I'd like to thank for this project. I'm especially grateful for Professor Daniel Eisenstein and Dr. Ben Johnson for mentoring me. I've learned so much from them, and I really appreciate their support. I'd also like to thank the entire JADES team for allowing me to use their data and their supercomputer. I'd also like to thank Erwin and all of my Astronomy 99 classmates and all of my amazing friends and family for the support. All right, thank you, and I'm happy to answer any questions. Yeah.
I just have a small question on the force flow slide. It just seemed like there was a lot of colors going on, and I was curious if that was just noise or significant.
Yeah.
What the different colors were representing.
Yeah. So this is kind of just noise. I think if you see like a very clear like blue region here, that indicates that we're missing something in the model. But the rest of this is just sort of noise that's not being picked up by the force flow model.
Okay. Gotcha.
So at the beginning when you were showing the histogram with redshift, it's not smooth. You know, there's this abundance of galaxies at a redshift of 6, and I'm just wondering what that means. Like in the next slide, you can really see it by eye. You know, there's a huge favored redshift here, and there's a big gap at redshift 4. Is that?
So this is partly due to the data sets I was using. So like going back here, Muse had a lot of like O2 and Lima alpha coverage, so there's going to be like a slight gap at like redshift 2.5. I think when we're getting to the higher redshifts, I had some pretty strict signal to noise requirements. I was trying to make sure that all of these SEDs had really good photometry. So a lot of these galaxies, well, there's a few that we observed and had spectroscopic redshifts for, but also some of them just didn't have a high enough signal to noise to include. And Fresco did find a lot of redshift 6 galaxies.
It's where H alpha enters the
Yes, that's what I.
data
That's
for
right.
Fresco.
So do we think the underlying distribution is, of course, continuous? And you're saying these are just selection effects?
Yeah.
Okay, that's right.
Yeah.
Is it just me?
Anyone else? Please.
I'm curious, so I know that from my understanding a lot of your work is developing a catalog for other people to use. What are some of the applications of an SED catalog?
Yeah, so there's SED fitting codes that can be used to determine photometric redshifts. I sort of went over that pretty briefly, but basically this library can potentially be reduced to find like some certain like key templates that then can be used to help determine photometric redshifts. Also, right now, like we're getting so much new data on these high redshift objects, so this can sort of serve as like a better reference for trying to look at like the stellar mass of high redshift galaxies. There's a bunch of other SED references like K corrections and stuff like that.
So you mentioned that you see some of the trends, for example, like the D4000, strength of the D4000 break, and then the specific star formation rate, the same behavior across redshift. Have you sliced up your sample by redshift to see if the trend has some systematic evolution that might have to do with things like metallicity?
So if I'm understanding your question correctly, I'm sort of hesitant to look at like high redshift and say this is a representative sample just because by requiring that they have known spectroscopic redshifts, it's sort of, they're incomplete. So I don't want to make claims saying like all of these high redshift galaxies fall within these metallicities or anything like that, just because there definitely are galaxies, particularly at higher redshift, that aren't being included in this library.
So I've got what's probably a naive question. Can you pull up maybe one of your spectra? Terrific. significant fraction of the flux is dominated by lines. And does that complicate the analysis in some fundamental way because you're doing photometry with a lot of flux in very narrow wavelength ranges?
Yeah, so it's definitely, with these very like young galaxies that have very strong emission lines, it definitely is complicated. I was trying to examine here like a really more continuous feature, so hopefully there aren't too many strong emission lines in that area, but it definitely is hard to go from like broadband photometry to developing like a best fit spectrum.
I definitely hold that thought until the talk.
Well, yeah, I had a specific question about this. You have this, I was looking at your plots, and this is anomalous point at 5,300 angstroms rest wavelength. Yeah, that guy. Is that just a really wide band, and it's capturing some of those emission lines, or is there something wrong with the models where you don't? Because in your next plot, that point is exactly where it should be.
Yeah.
So I'm just interested what's going on at 5,300 angstroms.
Yeah, so this point right here corresponds to this filter. This is a super, super wide filter and is capturing emission from here and from here.
Got it.
So we can see that the best fit photometry from Prospector given this model is here. So it is consistent with the green spectrum.
So it's that really wide.
Yeah,
so
yeah.
Explain it. Okay, very good, thanks.
Well, while we're asking about these plots, I'm interested. I've never used the model like is in Prospector, which produces the green lines here. So how many free parameters should I imagine are being fit for when you're developing a physical model of the spectrum?
Yeah, so we had a lot of free parameters. We were fitting for mass, for dust, metallicity. I think it was like 7 or 8 free parameters.
Okay, well, I think I have a more. Sam, late for this one.
Just come in a second here. Oh, because he said he wanted to talk.
Oh.
Okay, our next speaker is Brian Su. Brian is a joint astrophysics and physics concentrator with a secondary in math, so he's been covering a lot of ground. Brian has spent the last 3 years or so working on superluminous supernovae, various aspects of these very rare and most energetic type of supernova that we know about. He's published 2 previous papers on this topic in Nature, one on a study of the population from the Dark Energy Survey, which found the highest redshift superluminous supernovae that we know about. So Brian has looked at the question of whether the properties of these supernovae evolve with redshift. He then published a second study on superluminous supernovae that were identified not spectroscopically but photometrically using machine learning techniques. And so he looked at the properties of that population. And this is really kind of a pilot study for the kind of studies that we will do in the future with data from the Rubin Observatory LSST survey. And then for his senior thesis, he's decided to look at the question of trying to gain clues to the progenitors of superluminous supernovae by looking at high angular resolution images of their host galaxies from the Hubble Space Telescope, and then locating the supernovae within their galaxies to address the question of what kind of stars produce them.
All right, thanks, Ida. Hello, everyone. I'm Brian, and today I'll be talking about my thesis titled The Offset and Host Light Distributions of Superluminous Supernovae, Archival Deep Dive with the Hubble Space Telescope. It was advised by Professor Ido Berger and also Dr. Peter Blanchard, who was a former grad student of Ido's, who is now a postdoc at Northwestern. So before I start and go into the details of this project, I want to give you a little background about superluminous supernovae. So when I say superluminous supernovae, I really do mean type 1. So that means when you look at their spectra, they don't have any hydrogen features in them. And there are several defining characteristics for them. The most pronounced one is that they are extremely energetic and they can emit and radiate about 10 to 100 times more energy than regular type 1a or just core collapse supernovae. And they're also extremely rare, accounting for about only 1% of the volumetric rate for core collapse supernovae. And they also have very hot and blue spectra that are relatively featureless, and they preferentially reside in low metallicity dwarf galaxies. Since their discovery, there are a lot of questions that came up regarding the nature of these most extreme transients. So the biggest one is obviously what's their power source. There are several models that have been proposed, including the magnetar model and also circumstellar interaction. And there's also the question of whether we can use them as high redshift cosmological probes like type 1a supernova. And lastly, what are their progenitors and formation channels? So today I'll be focusing on the low metallicity dwarf host galaxy natures and using that to try and answer the possible progenitors for them. So some motivations for this project is that through the past decade of study on superluminous supernova light curve modeling with the magnetar model, we found that the magnetar model explains the light curves the best. So naturally, the next question is to ask, what kind of progenitors can make these magnetars? And then also, what kind of galaxies can host these kind of magnetars? But the difficulty arises for observations of their progenitors because they are usually at high redshift, extragalactic, so we can't really observe their progenitors. And we also want to know their connections to other type of transients with massive star progenitors, such as type 1c supernovae and also long gamma ray bursts. So with that, how do we do it? Well, we're going to turn to their host galaxies and use the property of their galaxies as a proxy to study the progenitor systems. There are several similar works that have been carried out in the past in using the host galaxies of transients to study properties of their progenitors. Highlighted in red here are work carried out in Ito's group in the past few years on different kind of transients. We see a very wide array of transients here. And then all of them measure some sort of parameters relating to the offset of the transient, and then fractional flux, which I will go into detail later, and also star formation rate and host brightness. And you might notice that there was already a study done on superluminous supernovae here, but then the problem with that study was that we only had 16 superluminous supernovae in that sample. And that doesn't give us enough statistical power to compare them to other transients and make conclusions about possible progenitor systems for them. So in this work, our overarching goal is to compile a bigger, larger sample for the offset and fractional light distributions to, number one, gain more understanding of their subgalactic environments, and two, enable a more robust comparison with other transients. So how do we do that? We do it with relative astrometry. So to do relative astrometry, we want to have a high resolution of their host galaxies. So we do that with Hubble Space Telescope images. Why do we choose HST? Well, partially because it has a wide wavelength range, including the UV, in which we can probe star formation rate. And also, thanks to its high resolution, we can resolve faint and compact tiny galaxies far, far away, which is useful for superluminous supernovae. And third, there are a lot of unused images since 2015 when the last study was done and taken with the Hubble Space Telescopes that we can utilize in this study. So after initial search through the archive, we found 83 available host galaxy images on HST that we're going to use in this study. So this is a breakdown of the rest frame wavelength probed, and then also the distribution of the redshift of these superluminous supernovae that we use in the sample. And we see that most of them fall under about 3,500 angstroms. So we're indeed probing the rest frame UV wavelength for these events. So to localize them, we also need to know where the supernova happened. So we obtained ground-based images for the explosions, and we want to find the deepest and highest resolution ground-based images for them. Most of our sample came from large surveys such as Pan-STARRS-1, the Dark Energy Survey, PTF, and ZTF. If an object is not part of these surveys, then we also utilize images from big telescopes like MMT and Gemini. So after we have all the images, we begin the process of astrometry. In short, astrometry is basically where you have two images that are taken with different telescopes that have intrinsically different astrometry system, and you want to align them precisely to know exactly the celestial coordinate of an object that you're interested in. So here, after we identify common sources between the supernova image and the HST image, we basically take the coordinates and match them together. We transform the coordinates from the supernova image onto the HST image because that's what we will be using. Unfortunately, in UV wavelength, the HST sensitivity is not as high as the optical wavelength. So some events, even though we have the images for them, we couldn't match them with relative astrometry. So at this stage, we are left with only about half of the sample, with 46 events surviving after this stage. So that's our sample size for the project. And in order to measure the offset of these transients from a reference point within their host galaxies, we need to first identify the centroid for the supernova. So using the supernova image, we calculate the centroid by fitting a 2D Gaussian and using the mean in both directions as the center. And we also want to quantify uncertainty onto that. So we measure the signal-to-noise ratio and also the fold-width half-max. And we estimate the uncertainty as the fold-width half-max over twice the signal-to-noise ratio. And then next one, we also want to measure a reference point within the host galaxies. So in this study, we use the flux-weighted center of the host galaxies. But before we do that, we need to first identify which pixels are part of the galaxies. So to do that, we do galaxy deblending. So on the left, you see the actual HST image, and then the red mark, the location of the supernova itself. And then on the right is what our deblending algorithm tells us is individual objects. So in this specific event, it is convenient that the galaxy is right behind the location of the supernova. So we do have a sense of where it is. But in cases where there are multiple objects surrounding the location of the supernova, we need to know which one is indeed the host galaxy. So we need to do some assigning. So this applies to instances where there are multiple objects, or if there are no objects nearby and the nearest object is very far away, we need to assign some number that tells us how likely an object is the host galaxies for a supernova. So we do so by calculating the probability of chance coincidence described by this equation. There is a lot of parameters in here, but sigma less than m basically is the galaxy number density in the optical wavelength brighter than an apparent magnitude of m, calculated by Ito a couple years ago. And then the other parameter that we're interested in is this RE, which is the effective radius, which we take to be the maximum of these two expressions. So the first one concerns our localization of the supernova, and the second one concerns the properties of the object that we're interested in. So in short, if our localization is precise enough, the first term will be really small, and the second term dominate, and we use the second term as the effective radius. But if our localization is poor, then the first term dominate, and you're just effectively using the same number for all the galaxy within that error circle. So here, using the same example, we calculate the probability for all the events in this frame, and then we want to take the object with the lowest probability to be the host galaxy of this supernova. So that tells us that event right behind the red cross is the galaxy that is least likely there by accident or by chance. So now that we know which one is the host, is most likely to be the host galaxy, we want to calculate the centroid. So we take the true host center to be the flux-weighted centroid given by pixels that are 3 sigma above the sky background of the image. And then we also want to quantify some uncertainty on that. But because of the irregular morphology of most of these supernova host galaxies, we can't just fit them with, say, like a Sirsic profile or just a 2D Gaussian. So we do the same thing. We vary the threshold from 3 sigma to the highest level that yields a detection. And then we take the standard deviation on that and quantify that as the uncertainty on the location of the supernova, on the host galaxy center. All right, so now that we have the location of the supernova and the host center, and also the uncertainties associated with them, we can now measure the physical offset. So basically, it's just the distance between the 2 points. It's fairly straightforward, and then we just convert that to angular size and then to physical scale using the pixel scale from HST, and then using the redshift to calculate the correct physical unit conversion. And then we also want to sort of capture the average host galaxy size for all the sample all the superluminous supernova in our sample. So we do so by calculating the half-light radius, which is basically just the radius of a circular aperture that encloses 50% of the Courant flux of the host galaxies. And then we do the same conversion to convert them into physical units. All right, the next thing that we want to do is measure this host normalized offsets. Why do we want to do this? Because intrinsically, for different transients, they have different galaxy sizes, right? So for superluminous supernova, we see that they're much more compact than other transients such as long GRB. So we want to be able to compare them and normalize it by the size of the galaxy. So we just divide the physical offset by the half-life radius to get this normalized offset. All right, so fractional flux. So why do we want to measure this fractional flux? What is this fractional flux? So the issue comes from that the offset that we measure is intrinsically a 1D measurement that does not take into account a lot of different things, such as the complex irregular morphology of these host galaxies. It doesn't take into account the viewing angle of the host galaxy, and it doesn't really tell us anything about the underlying distribution. So to measure this fractional flux, which was developed in 2006, the traditional method was we have this uncertainty error circle associated with the location of the supernova within the host galaxy. They take the area weighted flux to be the flux value at the location of the supernova, and then we sum all the pixels that are fainter than this flux value, and then we divide that by the total sum of flux within the entire host galaxy. And after we divide them, we get the fractional flux, which is a value between 0 and 1, where 0 means that your supernova is located on a pixel that is the dimmest within the galaxy, and 1 means it's located at the brightest pixel in the galaxy. But this doesn't really tell us how much this value varies, because sometimes the host galaxy brightness could be varying very fast, and if your supernova just happened to be sitting on that edge where it goes from very bright to very faint, then you are sort of doing a compromise, and that's not really a precise measurement. So we wanted to find a way to quantify this uncertainty somehow. So in this work, we do a Monte Carlo procedure. So because of the Gaussian nature of the uncertainty, we can construct a 2D Gaussian using the various uncertainties that we mentioned before, where x and y here are the pixel coordinates on the HSD image. And then we just do random sampling. We do it 1,000 times, and then whatever pixel it lands on, we take the flux value on that pixel, and we calculate the fractional flux this way. So in this way, we get 10,000 different value for the fractional flux, and we take the median to be the representative fractional flux value, and then we can also quantify the upper and lower error bar on that. All right, so now I've done a lot of talking about the methodology, and we can go into the result now. So before I show you the distribution of the offset, let me talk a bit about the math behind it. So if we have a collection of points with a standard deviation of sigma that are randomly distributed about a central point nu, and you want to find the distribution of the distance from a reference point, in this case the origin, you will say that the distance is distributed as the Rice distribution. And this is usually used for some positive definite quantity, such as the offset that we're measuring in this work. So if we just do some replacement, replacing nu with the offset and then sigma with the uncertainties that we have a Rice distribution as well. So if we take the distance from the centroid as the true offset and then the uncertainty associated with the area circle as sigma, then we can sort of do another distribution on what are the possible value of the offset for each supernova. So here is a cumulative distribution of the physical offset from our sample. So the red curve here has a median of 0.54 kiloparsecs, and then the gray shaded area underneath, we use the Rice distribution from the previous slide and do a Monte Carlo simulation, again 10,000 times, and we sort of do a density plot where the darker regions means there's a higher probability that that's the true offset from this, not the true offset, but like there's a higher probability that a single event will have that offset. And from that, it's not hard to see that our red curve sort of traces to the left of this shaded region, which tells us that after doing the simulation, the Monte Carlo simulation, our offset are actually being shifted to higher offset. And we do this, and we also plot the other transients as well, long GRBs, type 1c, and we can see that on average, our superluminous supernovae sample has a much smaller offset compared to other transients. We do this for the normalized offset as well. And we basically see the same thing where you have this shift to a higher offset value. And another thing that we're interested in when we saw this plot was to compare the distribution to a exponential disk profile. So the purple line here, it's kind of hard to see. It basically tells you if superluminous supernovae follow the distribution of an exponential disk profile for a galaxy, what the distribution of host normalized offset would look like. So it kind of traces that line, and we did some statistical tests to test whether they are drawn from the same population. We used the KS test and also the AD test to test this. So even though they have this similar shape in terms of distribution, we actually did not find a statistically significant event significance, which tells us that the host normalized offset for superluminous supernovae actually was not drawn from the same population as exponential disk profile. So that sort of tells us something. If both of the offsets sort of have this shift to a higher value, this is more likely for poorly localized events with a high uncertainty. And this also indicates that it is harder for us to find small offsets, because if you have a very small offset with a very small uncertainty, then that ratio is still sort of like around 1 or even above 1, and your offset is going to be pushed to a higher value. And you can visualize that by plotting the individual probability distribution. And so on the left, we show the probability distribution for the offset for each individual supernova. And then you see that on the leftmost, the green curve, even though it has a very small offset and the associated uncertainty is very small, you have this Y curve for the distribution. That's why some of these smaller offsets are being pushed to higher values. And on the right, we summed up the individual probability distribution and then normalize it. And you see that it sort of chases the exponential disk profile. And since these uncertainty are rooted from measurement methods, they shouldn't be any correlation between the uncertainty and the offsets themselves. But we do see a trend here. So we haven't done this, but here's a future work which I can talk about a little later because I think I'm running a little behind. But here's our fractional flux measurement, and I think it's fair to say when I first saw this and compared it to other transients, my first reaction was this. Because they look so drastically different from the other distribution, even compared to the superluminous supernova sample from 2015. So what is going on here? So in some other work, we did, for long GRB specifically, they did a area weighted ratio where you compare the area of the error circle that you have to the galaxy size to sort of weed out some of these poorly localized events. And when we do the same cut, we do see that we remove some of these lower fractional fluxes. But after we carefully review the images themselves, we saw that actually some of these events are pretty well localized in an absolute sense, but then they just happen to be outside of any galaxy. So we are not performing the same cut and just took the actual distribution to be the true distribution. And I think there is something to be said about this, which I'll come back later. And we also plot some distribution of the galaxy sizes, and we see that the half-life radius for superluminous supernovae are much smaller compared to core collapse supernovae and also lone GRBs. And when we compare the fractional light to the two offset distributions, we see that systematically you will get lower fractional flux at larger offsets, which makes sense because if you have larger offset, you're more likely to be outside of the galaxy, therefore landing on a background value, and you'll get a lower fractional flux value. And then we also tested some redshift trends. We didn't see any significant correlation, but one interesting thing that we saw was that in the leftmost panel, when we compare redshift to fractional flux value, we see that all of these fractional flux value of 0 sort of center at lower redshift, which is against our intuition because you would think that poor localization with low fractional light should happen at higher redshift where the uncertainty should be higher, or maybe because of sort of this edge dimming effect in the UV wavelength for host galaxy, but that is not what we're seeing here at all. So my conclusion so far is that superluminous supernova host galaxies are more compact and irregular, and many also display this evidence for interaction with other kinds of galaxies. And there's a strong correlation between the offset measurements and the fractional fluxes. And host normalized offset resemble an exponential disk, albeit not statistically significant. And also several superluminous supernovae seem to occur systematically outside of any galaxy. And there are a lot of future works to be, there are some questions that arose from the process of this research. Number one is how do we quantify and correct this effect of shifting to higher redshift due to this Rice distribution for the offsets? And if the host normalized offset traces the exponential disk, why does the fractional flux value look so different from any other transients? And the third one is low fractional flux values are more likely at low redshift. We want to investigate why this is the case. And then lastly, for those events that happen outside of the galaxy, could they be kicked out of the galaxy or could they be runaway stars before they exploded into superluminous supernovae? This is just a hypothesis at this point, but we are interested to test if this is the case. So the next step for this project is obviously to increase sample size. As we speak right now, there's a program that are observing more host galaxies for superluminous supernovae. And as I mentioned earlier, there are some cases where relative astrometry is unfeasible. So we will perform absolute astrometry by matching two images to absolute reference frames, such as Gaia or 2MASS. And then we want to figure out the way to correct for the observational bias and maybe perhaps even measure some other parameters such as the star formation rate, density, and the surface profile. And then we want to do a comparison with a magnetar engine parameters to see if any of these parameters have correlation with a magnetar engine model to help us sort of consolidate and confirm the theory that a magnetar engine is indeed the power source for superluminous supernovae. And then maybe, because I didn't mention this earlier, the astrometry performed in this project was not done using any existing software. We actually wrote this in Python ourselves. I spent about 80% of my time for this project working on the astrometry, and I think it would be very helpful if we can make it open source for everyone to use on Python. So this is the next steps for my project, and I just want to take this time to say thank you to Professor Ido Berger for supporting me through the past 3 years in research, and also Dr. Peter Blanchard for answering all my questions about this project, and also many other people within the Berger Cosmic Transients group. And then I think this is a perfect opportunity for me to announce what my next step is in the fall. So I will be attending the University of Arizona for my PhD in September this year. And with that, thank you so much, and I'll take any questions that you have.
Thank you, Brian. Questions? Yeah.
Yeah, so when you first calculated the fraction of flux with the whole like pixel identification thing, I was curious, when you do the distribution, the Gaussian, do you have enough ability to identify where in the pixel like it should be, or do you center that distribution on the pixel that it ends up in? Because I can imagine if it would be like close on the edge of a pixel, and you center the distribution on the center, that could mess with your flux. I'm just curious.
Well, so the idea is that many different points can end up in the same pixel, right? So I think we center the center of the pixel is defined at like 0.5 increments. So if it's within like like for example 1.5 to 2.5, then we take the same fractional flux for any coordinate that end up in that pixel, if that makes sense.
Yeah, I guess I was saying because I guess I don't know how precisely you can place the supernova, but I mean when you construct this 2D Gaussian, do you center that like do you have the ability to center like because if it was at that edge, then you get in the Gaussian you get about half your samples in this one or half in this one.
Yeah.
Do you have the ability to specify that?
Yeah, so this is, I think we just need to be consistent in this case. It's because if it's the case that it lands on the edge of 2 pixels, then you just need to have a consistent procedure in defining where the supernova is. But I don't think that has been an issue in the study because most of the astrometry have the supernova landed in a pixel entirely and not on the edge.
Okay.
Thinking about like when calculating the physical distance, you're projecting the 3D space into a 2D plane and finding the distance. I'm just wondering whether the third dimensional distance is important for your calculations and interpretations.
Yeah, so that is a good question. That is the problem why when I mentioned why we were calculating this fractional flux measurement, because it's not taking into that third dimension in terms of distance. So, for example, if you have like a galaxy face on, then the distance is pretty straightforward, right? But if you have some inclination to that galaxy in the line of sight, then that distance could be morphed somehow. So yeah, I think we are beginning to think about that a little more based on the results that we see and how to quantify that third dimension when we calculate these parameters. But right now, I don't have a concrete answer on that end for you.
Kind of similarly, you say you use the redshift to get physical distance. What are the redshift range? What's the redshift range of your sample?
It's 0 to 2.
We're calculating host probabilities. Are there cases where there's just no host, and how often does that happen?
There are cases where there's no host, but instead have a lot of different objects surrounding it. I don't know. Where is it? So, for example, it's not sort of like this, but there are objects in our sample where you have multiple objects surrounding it, and the actual supernova is located on a background pixel. So we still just take the lowest probability to be associated with that supernova specifically. There are some events that the host is not detected at a 3 sigma level, but rather at a 1 sigma level. In that case, then, in that situation, then there are examples where the host is not detected, where there's no object in, like, I think, 30 kiloparsec range. So in that case, we just can't use that because there's no host detected.
All right. Thank you, Brian.
Thank you.
I think there's a break scheduled. Yes. Congratulations on making the Arizona decision.
Yeah.
So I've done about 30 texts in the last 30 minutes from various neighbors reporting on their activities. From the rest of it was home working. Kids are disturbing. Ours are 6 and 8, and then there's sort of this sort of gaggle of older girls in the neighborhood. So, but 6 to 8 year olds, yeah. It changed as we went down the list. The point at which we were going to be most exactly. But like I'm very comfortable. And I have there's like one neighbor who's maybe 11 who's very responsible. So when she's with them, we don't worry at all. And she's been kind of hanging out with them today. So. She actually hired someone. Just let them roam.
resume our regularly scheduled programming. Our next speaker is going to be Serena Wormser. And some of you may be expecting someone a little shorter to be giving the introduction, but Mercedes could not be here in person today, so hello online to Mercedes. Serena is going to be talking today about a project testing effects of stellar activity on transmission spectra, which is a really timely problem and represents an important contribution to the field now that we have really high precision measurements from James Webb, and differences between our expectations and observations become more apparent when you have very precise data. Serena is a dual concentrator with astrophysics and EPS, and I believe your next immediate step is going to be a park ranger, right, for the National Park Service?
Yeah.
So very interesting joint thesis here with stellar activity and exoplanets. So take it away, sir.
Thank you so much for the introduction. So, as I was introduced, my name is Serena Wormser. I was working with Dr. Mercedes Lopez Morales on the problem of testing the effect of stellar activity in the atmospheric signals of planets transiting F-type stars. Now, before I go any further, I want to acknowledge two things. First of all, I just want to thank Mercedes for being an incredible research advisor and for being the reason that this thesis exists, and also being the reason that I enjoyed every step of the process along the way, which I don't think can be understated. The second piece that I want to acknowledge is the fact that this is a really long title, so I give everyone permission to call my thesis Medium Stars with Big Attitudes, F-stars being medium-sized stars. Now, this is an exoplanet thesis, and I want to set the stage a little bit with how far the field of exoplanets as a whole has come in the past 35 years. 35 years ago, we didn't know if there were any planets outside of our own solar system. We suspected it, but we had never detected one. The past 3 decades have shown this incredible progress from detecting single planets to dozens, to hundreds, to thousands. And in the current state of the field where we're at right now, we have over 5,000 planets confirmed, distant worlds with different environments, potentially different formation histories, exotic places that are nothing like the worlds in our own solar system. And in this environment, you can really go in 2 directions with this sample. You can say, let's look at the large-scale trends. We have thousands of planets. What are the populations like? But you can also look at each individual point on this plot of different detections, and you can say, well, what are the individual exoplanets like? What are their environments? That's what this thesis is. So this thesis is about characterizing individual exoplanets as opposed to studying populations. The main way that we characterize an exoplanet's environment is by observing and studying their atmospheres. Typically, we can study the atmospheres of transiting exoplanets. So transits are one of the main ways we have of detecting an exoplanet, and when an exoplanet transits, we're observing its orbit face on. So the planet, as you can see in a second, is going to pass in front of the star from our perspective. And as the exoplanet passes in front of its star, it causes a dip in the brightness of the star, just a tiny little dip, barely perceptible, but definitely there. And that dip tells us a few things. First of all, it tells us that there is a planet around that star. But it also tells us how big that planet is, what its radius is. It tells us the inclination we're looking at the planet, what angle we're looking at, and it tells us the period of its orbit and how far away from the star it is. These are all really critical pieces of information that we can already begin to use to characterize that exoplanet, but in some cases with transits, we can go further, and we can actually get the atmospheric composition of an exoplanet from its transit data. Now, this is just beginning to become widely used in the field. Our observational precision that's required for this is high. But in general, we can study a planet's atmospheric composition through a technique called transmission spectroscopy. I'm actually going to take about a minute to explain to you all how transmission spectroscopy works, because the remainder of my thesis relies pretty heavily on how the technique works. And so if we start at the top plot, you can see an exoplanet transiting, and this exoplanet has a puffy atmosphere. Now, the catch is that this atmosphere extends out to different heights depending on what molecule you're looking at. And we see the same thing on Earth. If we think about the Earth's atmosphere, we have oxygen, we have nitrogen, both oxygen and nitrogen puff out to different heights. What that means is at the wavelengths where one of those molecules, one of those atmospheric species blocks the light, the planet's radius is going to appear to be the regular bare rock radius, or whatever opaque radius there is, plus the height of that individual species in the atmosphere. Now, you have multiple different species in an exoplanet's atmosphere, and that means that at different wavelengths, your transit depth, the size of the planet, is going to be different. And so when you then bin transit depth on the y-axis and wavelength on the x-axis, you get the bottom plot, and that's what we call a transmission spectrum. This is one of several techniques used to study an exoplanet's atmosphere and environment. We just won't talk about the others in this 20-minute presentation. This technique has began to unlock atmospheric compositions of planets outside of our own solar system, but there is one big assumption that I showed to you all here that is actually an oversimplification at times. And that oversimplification, that problem, is the fact that stars aren't always a constant source of light. So when we observe a transit, it's not always just the planet causing the changes in the light. This is a picture of our sun behind me, and you can see that there's both bright spots called faculae, and then there are also dark spots called sunspots on the surface of the star. This is not only occurring in our sun. I think a general theme in astronomy is our sun is about as average of a star as you could get. Sunspots, faculae, occur in many stars. And in general, it's become a problem in the field of transmission spectroscopy that you might have either sunspots or faculae or both, and they're going to contaminate your transmission spectrum. In general, the name given to the source of contamination is called the transit light source effect. And depending on whether the star has sunspots, or I should say star spots, or bright regions, you're either going to get an over-exaggeration or an under-exaggeration of your spectrum, of what molecules are present and how abundant they are. This is a huge problem for when we want to start characterizing exoplanets as a whole, but especially as we're getting to more precise observations in smaller planets. This difference between the observed and true planetary spectrum can have a pretty large effect on our overall fit of what's in the atmosphere. Oh my God, I went too fast. So one of the other problems is that, the current state of the field is such that the transit light source effect is generally acknowledged in planets orbiting stars the size of our sun are smaller, and in particular, the smaller the star you get, the more spots become widely present on the surface of the star, and so it's acknowledged you need to consider stellar surface activity. But the current state of the field is such that it's believed that in stars larger than our sun, and in particular slightly larger than our sun, this no longer needs to be a consideration. You don't have the transit light source effect. My thesis says, hold on a second, I think that we might need to consider the transit light source effect in spectra of planets orbiting F stars, stars slightly larger than our sun. Of course, people have been thinking about this for a while, for longer than me, and they do have justification for assuming that you don't need to account for the transit light source effect. The next question that sort of naturally follows is why F-stars are not often considered to have stellar surface activity, or at least not enough that it could impact the spectrum. And the reason why is because when we observe the photometry of a star, so how that star's brightness changes over time, we don't see any change in the brightness aside from a very large dip, that's the exoplanet's transit. All of the error bars on the photometry are roughly in the same line. There's really no scatter. That this photometric curve, historically at least, has said no stellar activity. I do agree that this curve indicates that there's no star spots, but I would argue that there might still be faculae, or the bright spots on the star. To understand why, and to back up my argument, I just want to bring this a little bit closer to home and build up some physical intuition. And so what I have here, let's start with the star spot that I'm putting on a source of light. And you can see that this star spot has really high contrast. We can see how defined it is. But on the other hand, if I take a bright light, in this case a lot of fairy lights, and I put it on the same light source, it's still contributing to the overall source of the light, but there's no contrast. That light just blends into the overall bulb. And that's exactly what we see in stars as well as in a random lamp in my bedroom, is that you have high contrast on star spots and no contrast on faculae. Keep in mind, the effect is still there. You still have more light. We just don't see it as a defined point. Just in general, you can sort of associate faculae with bigger stars and star spots with smaller stars. That's a simplification, but for the sake of this presentation, it's one that we can go with. Because of that, because of the contrast, typically when we see star spots, we can see that star spots appear in the photometry, in the measurement of the light, whereas faculae don't appear in photometry, but we do detect them through radial velocity signals. Something I'm happy to talk about in the question section are the physical mechanisms of why. That's the main takeaway I want you to take from this. The other takeaway is that I did a little bit of field work. I was up next to my fan to get this picture. That's my fieldwork EPS component of this thesis. So, everything said. For my thesis, I want to ask, is a given atmospheric transmission spectrum affected by active bright regions on a star? We don't need to worry about the star spots. We don't see it in the photometry, but we might still see the bright regions. And in particular, I do 3 things in my thesis. The first act that I do in my thesis is that we actually develop a method to determine whether, with a given set of radial velocity and photometry readings of a star, whether a star is likely to have faculae on its surface. And then we consider 2 different case studies in applying our method. We apply our method to an exoplanet around an F-star to determine whether this particular F-star can host enough faculae to contaminate a transmission spectrum. And then, because we already developed a method, we also consider the wider applications of the method in the field of transiting exoplanets. I'm going to briefly cover my model here. I'm not going to spend much time on it, but once again, in the questions section, I'm happy to expand on our model. What we did is we took a pre-existing program called SOAP 2.0, where you can model stellar activity, and in general, the way that SOAP 2 works is you input the stellar parameters. So you say, well, I've got a star of this size, of this radius, etc. And you say, I'm going to put a spot on that star. That's this spot over here. And it's going to be a set size, a set temperature above the surface of the star, and at a set location in the star. And then SOAP 2 will do its magic and return the star's simulated radial velocity, photometry, and then 2 other observationals that we use to quantify how much activity there is. Problem is that SOAP 2 didn't initially allow for varying the temperature of faculae. It assumed a set value based on what's observed on the sun. So about 4 months of my thesis was spent adapting SOAP 2 to have variable facular temperature. And then that was the big adaptation we did. We did a few others, but inputs are, you put in the size, temperature, latitude, longitude, and then you return observables caused by that activity. And so that's what our model did. We ran every possible combination of an active bright region on a star, and for each single one of those facula of those active bright regions, we then compare the simulated outputs to actual observations we have of the star, both radial velocity and photometry. And then we say that a potential active bright region is allowed if the scatter produced in the simulations is smaller than the observed scatter, and it's not allowed if the simulations produce too much of an effect that we don't actually observe. And just keep in mind these 2 colors, because this is what the colors correspond to in my results. In general, you'll see yellow as allowed and purple as not allowed. That brings us to the end of how our method works, but now I want to talk about our 2 case studies and bring you guys into the results of my thesis. The first case study is looking at WASP 121, this ultra-hot Jupiter orbiting an F-type star, a star slightly larger than our sun. And we want to know if it's possible for F-type stars to have enough bright active regions to contaminate a spectrum. The reason why we chose WASP 121 is because it's actually the exoplanet that kicked off this whole project. we had a case in which we had reason to suspect that the transmission spectrum was contaminated. It was showing signs of the transit light source effect, but prior studies looked at the photometry and said there can't be star spots contained in there, which we agree with. There's no scatter. But if you look at the radial velocity, you'll notice that there's much more scatter than the error bars indicate relative to the best fit line. And the bottom plot of the radial velocity is the residuals. There's also a lot of scatter in the residuals. So to us, this is a bit of a smoking gun for potentially having bright active regions on the star. Given that, we ran our method with WASP-121, and these are the results. This plot is a lot to unpack, and I'm just going to walk you guys through it a little bit and then tell you my takeaways. So each individual subplot represents one input plotted against the other. So for example, you can have spot radius versus temperature, or spot radius versus latitude. And then the colors represent the percentage of times where each bright region is either allowed or not allowed by the data. To give you a more concrete example, we can walk through a particular case of, let's say we wanted to know if it's possible for there to be this really hot, bright facula, I should say, at a latitude of 60 degrees and with a radius of 0.5 r stars. So circular facula with a radius of half the radius of the star. Well, I take the point at 60 degrees latitude, 0.5 r star, and I can see 100% of the cases were allowed in the data. No matter what the temperature is, no matter what the latitude or longitude, you could have this extremely widespread spot there. And indeed, in general, only in extreme cases are faculae not allowed within the observational data of WASP-121. It doesn't matter how bright or how hot you made them. Just to put some physical context on this, faculae on the surface of the sun are only about 200 Kelvin above the surface of the star. So takeaways from WASP-121 results. First of all, you can have very hot and widespread faculae on the surface, although prior studies have excluded the possibility of stellar activity. And then, because WASP-121 has been used to set a precedent of not necessarily needing to account for these stellar activity in the transmission spectrum, our results also indicate that you do need to consider this effect for other transmission spectra of planets around F-type stars. These are already two relatively large ramifications, but I want to bring us in the last few minutes to another case study. To be clear, our central question has been answered at this point, but we had developed this method to take radial velocity and photometry and apply it to questions surrounding exoplanets. And so there are other cases that this is really useful. Another one that we could look at is TOI 1266, which is not an F star, it's an M dwarf. So we're going from stars larger than our sun to stars significantly smaller than our sun. And it's also not my project. This is work that is being done by Dr. Ryan Cloutier. Actually, I don't know how to say his last name, but he gets credit for most.
That's the way he says it.
Okay, fantastic, thank you. Yeah, and TOI 1266 is a system with two transiting exoplanets, one that's transiting sort of close to the equator and one closer to the pole. The super weird thing in the system is that the transit depth changes in between observations for TOI 1266c and doesn't change for TOI 1266b. There's a few hypotheses as to why this happens, but one of them is that you have a bright active region close to the pole of the star that sort of ebbs and flows season by season. It gets bigger, it gets smaller, maybe it changes location, and that's when my method comes in, because we can look at the observations of TOI 1266 and ask, is it possible for faculae to be contained within TOI 1266's data? Don't worry too much about the outputs aside from looking at the fact that instead of being mostly yellow, the results are now mostly purple. That means in general, there's a lot less activity, a lot less faculae are allowed on the surface, but notably, if you look at higher latitudes, especially close to the pole, you can see that it is possible for there to be faculae contained within the data. It also makes sense that there's not too many faculae allowed with very hot temperatures because it is an M dwarf. major takeaway, there's a possibility of polar faculae. And then we can even go further and split up the observations into multiple seasons because we are expecting seasonal variability if this hypothesis is the cause of changing transit depth. And we can look at if activity changes season by season. We don't have results yet, just because this is in progress, but I mostly use this as an example to show how our method can be applied to cases outside of just F-stars and outside of just transmission spectroscopy. This brings me to the end of my presentation. And just to summarize everything all together, my thesis developed a method to determine whether faculae are plausible on a star. It doesn't tell you an objective yes and an objective no, but it tells you if it's plausible. We then showed that WASP-121, given its photometric and radial velocity activity, plausibly contains widespread bright active regions on the surface of the star, which means you need to go back to the transmission spectrum and consider the transit light source effect. And finally, the method we developed has uses and implications outside of just transmission spectroscopy and outside of just F-stars. So I know that I just want to wrap up by saying that we are at a very exciting point in the study of exoplanets and in the study of atmospheric characterization, where we have new tools, new instruments that we can use to look at smaller planets, to look at even potentially rocky planets like our Earth, and to characterize them. And this is the direction the field is going in the future. And in doing so, it's incredibly important that our observations of these atmospheres are accurate and that we're able to account for sources of contamination and processing. And that my thesis just seeks to do a tiny little piece of that and to contribute to that overall goal. Everything said, thank you so much, and I'm happy to take any and all questions you may have.
Are there any questions?
Yeah, Chris.
So why would you expect to not see faculae showing up in a light curve, like as opposed to a star spot? Because if you're just adding, like say you're adding 1% flux and then it's moving around, versus subtracting 1% flux and then it's moving around, what's the difference there?
Yeah, so that goes back to the question of contrast, which is actually already conveniently located on here. And with faculae and in general, like you are increasing the overall flux of the star, but you're not necessarily like there's no contrast. And so in between measurements, I would say the biggest difference is that like it's an overall net brighter experience, but sorry, let me think about rephrasing this slightly. If you think about photometry as measuring like a snapshot of the brightness distribution of a star when you look at it, and then you think about radial velocity as measuring like the hemispheres, that's a helpful way of thinking about it. I would say the best way, if you allow me to go back on rambling and actually, I just came up with a better answer. Star spots notably reduce the brightness of a star. Faculae have a small contribution to the flux, but a larger contribution to how they impact the magnetic fields of a star. And so active regions in general suppress magnetic fields, or have high magnetic fields which suppress the convective blue shift effect, leading to higher redshift. And so you have like strong indicators of faculae and radial velocity because your magnetic fields become into effect, whereas the flux effect is smaller. And I just didn't have time to go into that in this presentation, which is why I think you picked up on a good place to ask a question.
So even though it might be smaller, like light-wise, it makes a big difference in blue shift redshift.
Oh yeah, no, the radial velocities are heavily impacted. Here's an example, is this plot on the bottom left. You can see the blue curve is radial velocity without a notable facula, whereas the yellow curve is a facula with a temperature of 500 Kelvin above the surface of the star. And you can see that there's no blue shift left. Like the radial velocity is just a redshifted curve. Yeah.
Do you have any other questions?
You hinted at it a little bit with the seasonal plots, but like how long are faculae supposed to exist?
Oh, fantastic question. I haven't the slightest idea. Yeah, that's something that I should know, and I don't. It's a good question. Yeah?
Any other questions? I'll ask one.
Please.
So since this work is focused on F-stars and the contribution of stellar activity around F-stars, thinking about the types of planets that people take transmission spectra of around different types of stars, it seems like there are a lot of small planets around small stars because those are where the signals are largest, and fewer small planets around F-stars. But there are a lot of giant planets around F-stars. Can you talk a little bit about like the magnitude of this effect that you'd expect in like transmission spectra versus sort of how the models and data are agreeing in early examples from James Webb, if that's something you've thought about at all?
Yeah, so I haven't thought about it quite as much in the context of James Webb with smaller planets, but I have thought about the magnitude of the effect a lot with large planets around F-stars, and the effect is noticeable. It depends on the actual scope of the effect, but if you look at the actual transmission spectrum of WASP 121, so this is where you look at how the planet's radius RP over R star changes relative to wavelength. You can see that the purple lines of best fit for planetary atmosphere models deviate really significantly from the observed blue points in that slope. And that's what initially told us that this might be affected by faculae. So it's not an insignificant effect. I just don't know the magnitude relative between like small planets and large planets, which I think was your question.
No, this actually answers my question. Really.
Awesome, sick. Yeah. No, it's like a large effect. It's not small.
Okay, any other questions? All right, let's thank Serena again.
Yeah, thank you guys for listening. Oh, I'll also add, I thought I got really lucky with the timing, so I hope everyone enjoyed the break. Lucky with the timing of talking right after the break, I should say. So, enjoy.
Pull back to the start.
Sneak break.
Okay, well, I was very lucky this term to have 3 of the seniors working with me for theses, and this is talk number 2. But these are all focused in the topic area of using the new data from the James Webb Space Telescope in and around the ultra deep field. These are extremely deep images and spectroscopy of faint galaxies. And so Katie Sharp has been working to study the clustering of these galaxies. Clustering is something that we do a lot of at low redshift, but when you get out to high redshift, you might have thought that the universe would be much smoother and simpler, but in fact, it turns out that it's about as complicated as it is around us, but we're only now getting to samples that are big enough to be able to really study that. And so that's what Katie's going to tell you about.
Thank you for the introduction. As you may be able to tell, my thesis is on the clustering of high redshift galaxies, high redshift being about redshift 7 here. And as Daniel mentioned, this is a really exciting, somewhat new thing we can do with JWST. So here's a quick overview of the structure of my talk. So I'm going to give a little bit of context on the universe as well as JWST before going on to my results and my method. Right, so here we have kind of a diagram showing the history of the universe. We have the present day over on the left, and then the beginning of the universe and the Big Bang over on the right. So it's a little confusing because time is evolving from the right to the left, but bear with me here. So we have the Big Bang in the beginning, and then there was the hot plasma-y soup. That's the orange bar here. Before we have the cosmic microwave background, which happened during recombination when suddenly the universe was no longer opaque to the passage of light. Then there was the cosmic dark ages before any real stars or galaxies formed. It was just molecular matter hanging out. we have the first stars and galaxies appear, and this really kicks off this cool epoch, which is the era of reionization. Reionization is when all of this matter that was like molecular suddenly becomes ionized again. And we think that's due to the ionizing sources from the first stars and first galaxies. Then a bunch of galaxy evolution happens as we go towards the present day, where we see like modern galaxies and like the modern universe. This is a tiny bit outdated because we still have Hubble over here, which is no longer our best tool for studying the universe, but I'll get to that later. In this study, we're really looking at redshift about 7. It's really like 6.4 to like 8.2 or something like that. But that lands us solidly right near the end of reionization on this plot. Reionization, it's really cool because, as I mentioned, this happened because of the first ionizing sources, like galaxies. So we're really looking at the earliest galaxies with this. Yeah. I just want to briefly mention, I've said redshift a lot, and I have some friends and family who are non-experts. So when we're talking about high redshift, we're really talking about both old and really far away stuff. So light has a fixed speed. Things that are farther away, the light takes a longer time to get to us. If it's traveling 13 billion light years, it's taking 13 billion years to get to us. Redshift happens because the universe is expanding. So you can think of it either as there's more universe that is expanding between us and an object, and thus the object appears to be moving faster away from us, or we can think of it as like light being stretched by the expansion of the fabric of the universe. So either way, you want to think about it like that. Moral here is higher redshift farther away, older from our point of view, older light, earlier universe. Right, let's go on to JWST. So I'm sure if you've been here, you've heard multiple talks mention JWST. I don't think I need to tell you why it's such a cool thing to have. The James Webb Space Telescope is the new space telescope. This is what it looks like. It's in space right now doing observations. It's very cool in the fact that it both has a larger aperture and is also has a higher resolution than like something like Hubble. So that means that we can look at fainter objects as well as look at these objects in more detail. And also the fact that it's IR, if you'll remember from Maya's talk, means that we're looking at things that were rest frame optical. So they were emitted in the optical before they were redshifted towards us. And this is especially good for looking at the high redshift universe, which I will also get to in a minute. JWST has multiple scientific instruments. We really only use NIRCam here. These are just a bunch of filters that NIRCam has in order to observe at different wavelengths. I will also get back to how this applies in a minute. NIRCam is kind of a strange like detector situation. So if you look here, there's like this short wavelength channel on the left-hand side and the long wavelength channel on the right-hand side split by this black bar. And really that is how NIRCam splits things in order to observe them. So it splits the shorter wavelengths onto this like blue channel, has a little like gap there, longer wavelengths onto the red stuff. And that makes planning like a survey a little difficult because you have this really weird detector layout that you're putting on the sky. There's gaps everywhere. If you just want to look at like a solid square, it's not as straightforward as something like Hubble, where it didn't have this going on. Yep. So moving on to the methods, we are using data from JADE. So this is the JWST Advanced Deep Extragalactic Survey. And we're specifically looking at the Good South field. So the Good South stands for the Great Observatory's Origins Deep Survey. This has been observed by a bunch of different like NASA Great Observatories. So it's a really rich field. I'm just looking at JWST data, but there's a lot going on in this field. This is the observing footprint that we have, approximate. There's been some changes since when it was first planned, but this is approximately like the redshift declination that it was observed at. This whole observing footprint measures about 75 square arc minutes, and that translates to 225 co-moving MPC over H square as an area. I will mention briefly, we use H here. This is a kind of standard thing in cosmology. h is h naught, the Hubble constant, divided by 100. And we're using, I believe, a value of about 0.67 for that. So that's, that's the value of h naught that we're going with. We're looking at this area with NearCam in JADES, and JADES really uses mostly these wide filters. There are some areas that have like more filters involved, but for consistency's sake, we're trying to use the filters here that have been used throughout the entire field. And for those filters, JADES uses most of them, but notably not like the shortest, the bluest one. So our lowest filter is really FO90W. And this is important because FO90W is uniquely suited for studying the redshift 7 universe. As an explanation for that, in order to determine if a galaxy is at a certain redshift, it's not really like a straightforward thing to do. You might remember back to Maya's talk where she was looking at SEDs, kind of trying to model the emission spectrum of galaxies. So it's not really normally straightforward because we have a bunch of filter bands and not like this detailed spectrum going on. But it is possible to determine pretty well for specific types of galaxies, and that is this Lyman break or dropout galaxy. So you can see here, this shows that there's a Lyman break right there, and the light just completely disappears beyond a certain wavelength. And for redshift 7, this just so happens to be right near our FO90 filter, which is about 0.9 microns, which falls right at the edge there. This also shows why JWST is so uniquely situated to study this high redshift universe, because if you look at the plot here, Hubble is the blue area, and that just completely is below the drop. So we can't really see these galaxies at all just with Hubble, necessarily. So dropout galaxies, this occurs because light from the galaxy is being absorbed by like hydrogen between us and it. And I think this is a really good plot that really shows how we can actually find dropout galaxies using JWST. So this is from a recent paper by Tuchella et al., 2023. And you can see these are the different wide and like a few medium filters that we have from JADES, JWST. And if you look, this is a dropout galaxy because the light between F150W and F115W just completely vanishes. So it completely drops out between these two filters. And that corresponds to a wavelength, this corresponds to a higher redshift than what we are interested in. But it is very cool because it is a very distant galaxy that we found. This more shows like what we're actually looking at, which are FO90 dropouts. So you can see here, I go like this. There is light appearing in F105, but then there's no light appearing in FO90. Kind of go back and forth there. This also shows how we can fit SEDs right there in order to find the photometric redshift. And this is a photometric redshift program called EASY, which produces a redshift of about 7 for this galaxy. So we can apply this broadly across all of the sources that we find in JADES, and we end up with about 700 dropout galaxies at redshift 7, which is really cool because this is like the most massive sample I'm aware of at such a high redshift. And it's just really cool. Really exciting for the field in terms of like our ability to detect high redshift galaxies. Yeah, and there's the more precise redshift range that I've used here. So how do we go from this like list of RA decks, or here I've done like pixel values on the detector, to something that tells us about clustering? Well, we need a randomly populated sample for comparison. We need to determine whether something is overdense or underdense by comparing it to something, some baseline. And the way we've decided to make a baseline is by determining like how likely it is to have detected perhaps a random galaxy in a location. So As I mentioned before, NIRCam is kind of a strange instrument. You can see the little like tiling here. There's different depths of imaging in each of these different regions, and that's important because we think it's more likely that we found a galaxy somewhere if it's more deeply imaged there. That just kind of, kind of intuitively makes sense. So what we've done here is we've really taken the observing footprint over there. We've masked out a bunch of bright sources, so like nearby galaxies. You can't really see it, but that's what the middle panel is. And then we've taken the imaging time in the F090 field, or filter, and applied that over the mask. And now with these weights, we're able to say something about how likely it is to have determined that there's like a galaxy at a certain pixel. So we can then randomly populate it. We do this with a power law. I'm not going to go into the details, but we like take the number of galaxies that we did detect in each of the different regions and do a best fit to determine what the power law would be, and then we can randomly populate it like this. And it seems fairly representative. You can see that there's much more galaxies in the like ultra deep area, way fewer in the more medium area. So relatively decent. I want to briefly mention error before we go any further. There are a lot of complicated ways to measure error with like covariance matrices. We just assume that it's Poisson, so galaxies are like randomly distributed, and we take that as an upper bound on error, and then we've used the 1 sigma error for like the rest of this from that. Great, on to results. So first of all, we've used the clustering statistic of delta W. This is slightly different from the 2-point angular correlation function that some of you might be familiar with. We do this because there is actually like larger baseline variations in the selection function. So we've wanted to more tune towards like lower baseline stuff, which we think that we've modeled fairly well. So we've used this one. This is the big money plot, moving right into my results. Here we've plotted delta W as a function of theta, and yeah, it's pretty cool. This is in log. That is because the function drops off as a power of like theta to the -1 due to how you calculate any kind of correlation function. And so we might think that maybe it's a good idea, instead of having it as like a slanted line here, you can multiply this entire thing by theta, and then it should in theory be maybe more flat, which we've done here. And yeah, I think this is the main result of the paper. So this function here is fairly flat. We've put the best fit flat line here. And I think it's pretty cool. This also excitingly hints towards something. So if you look at the shape, you can kind of see there's like 2 peaks vaguely. That is important because though it's not like completely determined by this that this is a true effect, not just something like from air, that excitingly points towards this known thing about galaxy clustering, which is that there's 2 components, galaxies that are clustered within the same dark matter halo and galaxies that are clustered in 2 different dark matter halos. These are known as the 1 and 2 halo terms. This plot kind of shows that, so this is also a W plot, not flattened the way I flattened the last one. But there's the 1 halo contribution and then the 2 halo contribution. And perhaps that is what we're seeing here. If so, that would point towards like our knowledge of more nearby redshifts kind of also applying to these more distant redshifts. Yeah, the other important thing here is the amplitude of galaxy clustering. So that's like the value of the y of this flat line here. This amplitude allows us to actually approximate to 3D how fast clustering falls off. So psi here is the 3-dimensional 2-point angular correlation function. We generally model that as an exponential of this form. Yeah, so we can approximate that with the Limber approximation using both the value of clustering amplitude, which we found already, and a distribution in z. Confusingly, this z is not redshift, but is rather co-moving distance. But we can take the photometric redshifts that we found using the EZ protocol from earlier, and we can plot those as just a number density over the co-moving distance. And then we can also take the amplitude, and we can solve for the scale length, this little R0 term, to determine how fast clustering drops off. I want to quickly add that this value that we find is consistent with literature values. So this is from a study, Zahavi et al., 2011. And our value that we find is right in the ballpark of like order 1 to 10 values that we also find at other redshifts. Now, the question is, what does this all mean? And how can we apply our observations to our understanding of theory for cosmology? So in order to do that, we've also taken this simulation. So this is the Abacus Summit simulation suite. We've taken one specific one at redshift 8. It's not just a redshift 8. It is a gigaparsec over h cube. So it also goes to cover our redshift range that we're looking at. This simulation has a total of a lot of particles, 4 times 10 to the 10. Each particle has a certain mass associated with it, and we can cut such that we create clusters of these particles into halos, dark matter halos. So these cosmological simulations trace dark matter in the early universe. Yeah, so once we've created our halos, we can then claim something about how we populate galaxies into halos. There are more precise ways to do this. We randomly place a few satellite galaxies into halos. The main thing is we have at the center of every dark matter halo, we have a central galaxy. And yeah, even though we randomly place satellite galaxies, this is sufficient for our purposes because we're just trying to get the fact that there is a one halo term into the following plot that I'll get to. So that suffices to do that. This is not the following plot I meant. Anyway, this just shows where dark matter halos are from the simulation. Actually, this shows where we've placed galaxies. So there's the central one in each dark matter halo, and then a few randomly populated ones as well. You can see that's the scale length. If you remember back to earlier, I don't think I said, but I had on a slide that it was 225 square h to the -1 MPC in area for our survey. So each of these little boxes corresponds to about that size. And if we go on, this is the plot I was mentioning. So this is once again showing our theta times delta W. We've done that for the survey in purple. And then we also have the simulation. The main one is this lighter blue. So that shows with the satellites also populated. I've also included without it just for completion's sake. And you can see, excitingly, that we are able to reproduce this amplitude of clustering, this red line now here. And so this is exciting because it means that our observations are possible. It is possible to recreate the observations using simulated data. So our observations are consistent with our theoretical framework for this regime. And as I mentioned before, the 2-point angular correlation function in 3D, this value of R0 can be derived based on the amplitude of clustering as well as the distribution in co-moving distance. And so we are able to essentially recreate that as well using this. Great, so I'm going to end it with a few conclusions. First of all, the clustering statistic is approximately flat and also hints towards possible 1 and 2 halo terms. The break there, which I didn't really mention as I was doing it, but this break here is at about 0.3 MPC h to the -1. That, as I didn't mention earlier, but that may correspond to about the order of the diameter of a dark matter halo. Right, scale length in 3D, we find the scale length of the 2-point angular correlation function in 3D. I've put that value there. It's consistent with other studies, so that's also very cool. And then finally, when we compare to simulated data, we find that our observations can be consistent with the theoretical framework. The minimum halo masses for that we need to reproduce the observed data is about 10 to the 10 msun, which I believe is also consistent with other literature findings there. Great. There is more space for future work, so this study only uses data from GOODS South. JADES is also looking at GOODS North. That's more recently taken data, so I didn't have time to get in this presentation, but it would be cool to also extend this project to include that. Also in the JADES data, we have the possibility to look at higher redshift samples. The sample size drops off when you go to like even the next higher filter, F115. But we could still go forth and do the same kind of analysis on that kind of data. And then also, I did mention that we randomly populated satellite galaxies into the dark matter halos that we got from the simulation. There is a more detailed and precise way to do this by like actually looking at like subhalos inside of the dark matter halos. So that could be another avenue in order to determine if like it's actually consistent or if I just happened to accidentally come across something. Great. I have a lot of people I'd like to thank: Daniel Eisenstein, Ben Johnson, as well as Maya and Natalia. I want to thank my readers, Lars Hernquist and Doug Finkbeiner, and then additionally my friends and family and everyone in Astro 99 class for being here the whole time.
Okay, time for some questions. Please.
Yeah. Do you mind describing, like, physically what the difference is between the 1 and 2 halo stuff? I just didn't quite get what that was.
Can I draw on the board?
Yes.
Pictograms, maybe. I don't know.
Okay, so imagine there's a dark matter halo here, right? Inside of the dark matter halo, there's not necessarily only one galaxy. So we have one at the center, probably. That's like the most likely location for something to be. But then there are also other galaxies that are associated with like subhalos inside of this dark matter halo. And thus, we expect that there's clustering within the scale of the dark matter halo itself between like those different galaxies that populate it. So that's the 1 halo term. The 2 halo term is when there's 2 dark matter halos like next to each other, and then there are galaxies inside of that, and that radius is associated with clustering as well.
Okay, yeah, that was super useful.
Okay, cool.
Can you go back to the main figure thing that you have with the purple bars? Yeah, that one.
This one?
Yeah. So I'm seeing it like on the far right side, there's like a pretty significant spike there. Do you know what that is? Is it like an artifact, or is there potentially something else going on there?
Yeah, I wouldn't be surprised if it was an artifact. As I said, there's like larger scale variations. Once you go really high, if we go back up here, so keep in mind this is about 70 arc seconds over there. Then when we go here, this is like 129, so it's about half. So I personally, my hot take is that there's some kind of like square thing going on with our model. Yeah, that's my take on it.
At the risk of being persnickety, you said about 5 minutes in something about Poisson errors and the lower bound on the, an upper bound on the uncertainty. And I was thinking there should be a lower bound because, I mean, you at least have uncertainty from the fact that there's a Poisson something galaxies sprinkled on your selection. There could be errors from other things too. So did I mishear, or am I missing something?
It's some kind of bound. Maybe Daniel would know better than me.
I think it is lower. I mean,
it is lower?
Yeah,
okay.
The sample variance will kind of give more.
Okay. Just checking.
You mentioned in the end that moving to higher redshifts is something you could do in the future, but the sample drops off quickly. How much does it actually drop off? I don't know, order of magnitude? And are there other people working on this? I imagine that it's a very crowded field in the, well, not intended.
I'm not sure exactly how much it drops off because I haven't looked at it. Daniel might know. I know there are people in JADES looking at higher redshift stuff. There's actually like a lot of papers going on right now. I don't know if anyone's looking at clustering though, specifically.
We lose about a factor of 10 at read delta Z of 2 or 3. So it's crashing down. And, but this is the best data set for doing it, so we have a shot. Are there other questions? Go on.
So very soon, so that was a very nice talk. I was curious how you would incorporate spectroscopic redshifts into this analysis, because soon you'll have, like several hundreds of galaxies for whom we actually know the spectra, like the redshift, like very precise level. So have you thought about how you would like fold them into this, or refine this by using that information?
Yeah, so for now, the way that I've modeled like PZ here is with the photometric redshift, and I've actually gone ahead and like smoothed it with a GKDE here, because I assumed that it was like approximately on par with what it would be, but I think a more precise thing would actually help a lot with like determining the actual value of the scale radius.
So you could basically put in like kind of like delta functions into that kind of plot and it would still work.
I think so. Because really the way that we work with this is we integrate and then there's a function of this, you integrate over it. So I think a more precise method there would actually help fairly well with determining this.
Cool, thanks.
That's really the only place I'm using like the specific redshift though, so.
The issue is that it enters, the formula she didn't show you involves this thing squared.
Mm-hmm.
So noise
does affect it, yeah.
The noise can be a little dangerous because it will enhance the structure in a way that's false.
Mm-hmm.
So you want to be a little careful.
Yeah, I didn't really go over the nitty-gritty of different calculations that I've performed here because, this is a short talk and also there's some non-experts who I've invited, so yeah.
One last question. Okay, well, let's thank Katie one more time. Here in the trio of students who are working with me this term. Very happy to introduce Natalia Villanueva, who has been working on really trying to understand the details of these emission lines that you've been seeing coming up in some of the earlier talks. So again, big thanks to Ben for all of his help on advising these students. So, Natalia, please take it away.
Yeah, thank you for the introduction. So I'm Natalia Villanueva. This has been a fantastic learning experience, getting to learn how to work with the James Webb data and get to explore some of these emission lines to probe star formation. So many thanks to my advisors, Daniel Eisenstein and Ben Johnson, for all of their help. But today, I'm very excited to be sharing with you what I was doing this year for my senior thesis, which is probing the star formation of galaxies between redshift 4 and 5 that are really beautifully morphologically complex. They have some really great substructures and components in them. So we're trying to use H-alpha and rest UV emission to create pixel scale maps and kind of probe how we can connect these morphologies and star formation properties together. So just to quickly outline how the talk will go, I'll begin with an introduction about what it means to trace and probe star formation with H-alpha and rest UV continuum emission, and then mention why JWST is critical to be able to probe star formation for galaxies at redshift 4 to 5. And then my thesis work can be largely separated into two different components, the first being identifying which galaxies in the images do emit this H-alpha line emission, and then the second component being actually creating these maps of the H-alpha and rest UV continuum emission on pixel scales. So to begin with the introduction, star formation can be probed. It's very much a multi-wavelength problem, so we can use everything from radio to X-ray wavelengths to be able to understand different stellar populations and different properties of the star formation process. But for my work, I focused on two main wavelength ranges. The first being the rest optical wavelength range. And I'll kind of explain this diagram first because it really encompasses the premise of how we can use both the rest optical and rest ultraviolet wavelengths to be able to study young star formation. So if we're trying to think about the star formation and star formation rates of stars and galaxies, we want to be trying to probe largely the most recent instantaneous star formation that's happening in those galaxies. So to do this, we have to look at young stars because those are ones most recently forming. And these young stars are hot, so they're emitting in the UV radiation, so pretty energetic emission. However, as part of their star formation process, these stars are also really enshrouded by gas and dust around them. So this UV radiation, some of it will get obscured by this dust and re-emitted in the infrared wavelength range. But the other ultraviolet radiation coming out of these stars will take that hydrogen gas that's surrounding these stars and ionize it, meaning it's stripping the electron off of those hydrogen atoms. And this actually allows the atoms to go searching for another electron to recombine with, which is that recombination process that I'll talk about in a second. And then those hydrogen atoms that have now recombined with an electron, like we see up here kind of the different energy levels of a hydrogen atom. The electron will start cascading down as it's searching for a more stable ground state. And as it's cascading down the energy levels, it'll start emitting radiation at other energies. So, like I mentioned, ultraviolet wavelength range, we can probe the star formation of these young stars by trying to probe, that kind of direct emission. But it's also, like I said, quite sensitive to the dust around these stars. And then we have the rest optical, which is where the energy from that cascading down the energy levels comes from. And those are called the Balmer series of emission lines. So I'm specifically interested in the H alpha emission line, which is that n equals 3 to 2 transition in the energy levels. And H alpha is a really great probe for instantaneous star formation. So what the rest of the thesis will kind of entail, and especially trying to map these two different types of emissions, is that with H alpha, we can probe that young star-forming population. Ultraviolet, since it's actually slightly lower in energy than that H alpha line emission, we'll be probing, compared to the H alpha, at least slightly older star-forming populations, but also we can use the comparison between the two to also start to get insights and an understanding into that dust that's enshrouding these stars. So to be able to probe the redshift 4 to 5 range, that means that the H alpha line is going to be redshifted from the optical into the infrared. So that's where JWST comes in. It's incredibly exciting that JWST is not only finally able to give us the observational capabilities to actually probe this region where the H alpha emission is being redshifted into with its infrared filters, but also that JWST can really incredibly spatially resolve its images to the scale of 0.031 arc seconds per pixel. So that means that we really have this great combination of observational capabilities to both probe the star formation and try to understand the spatially resolved morphologies we're seeing in these galaxies, how that's connected to the star formation too. And like has already been mentioned, we're the JWST fan club over here with the JADES program. I was using specifically data from the Good South region and NearCam images for all of my photometric work. So, getting into now how I actually chose the galaxies from the image that were emitters for H alpha line emission. These were the three main filters that I used to be able, in the technique, to be able to identify the H alpha line emitting galaxies. And Katie gave a great overview of the different filters for JWST. So what we did was, if we're interested in finding the H alpha line emission that's redshifted into the range of 3.5-ish microns, that means that this filter that's centered in green here, centered at 3.56 microns, is going to be a great place to look for these H alpha line emitting galaxies at redshift 4 to 5. and how we can go about identifying which galaxies are showing an excess emission, flux emission in this green wavelength range covered by this filter is we can kind of set a flux continuum with two adjacent filters, those being the red and the blue filter here, centered at 3.35 and 4.1 microns, and use that to set a baseline from which we can try to measure the excess emission that we're looking for in this green filter here. So we're kind of looking for the excess emission right there where the filters are not overlapping. So we went about setting, trying to mathematically model the flux continuum with a power law. So up there at the very top is a flux density modeled as the power law. So we have a normalization factor A, and then we have the power law slope N as the two parameters there. And we can do some integration of the flux density to actually achieve a photometric flux that we can use this technique with the fluxes from the JADES images. But the really key point here that allows us to identify some excess in that 3.56 micron filter is that we can add this extra term to the flux model there, the parameter L, which corresponds to the excess H alpha flux that we're looking for. And what we can do when thinking about how we take this flux continuum model, which after doing some of that integration and with the properties of the wavelength bounds for each filter, we can use this filter model and set it for each of the three filters that we're interested in using for the flux continuum. And we can force L, that excess H alpha flux parameter there, we can force that to be 0 for the two kind of anchor filters that we're trying to use to set the baseline continuum. And then we can allow in the 3.56 micron filter where we're trying to find that H alpha excess emission, we can allow L to be greater than 0. And this parameter L is ultimately how we characterize how much H alpha line emitting flux there is for any given galaxy. So how I went about actually identifying what those parameters A, L, and N are for the power law continuum is performing a chi-squared minimization fit for each galaxy, and then looping over that minimization for all of the galaxies in the image, and that leads us to a catalog with the parameters for this flux continuum model for all of the galaxies in the image. And then this just visually kind of shows what I'm talking about here, saying that L equals 0, that there's no excess because you just see that power law continuum there. So this is a non-H alpha emitting galaxy compared to here I show a galaxy that is H alpha line emitting, and we can see that L is greater than 0. So we see that excess in the middle 3.56 micron filter band. So after I made this catalog with the power law flux continuum parameters for each of the galaxies in the image, we of course wanted to select to find which ones were the H alpha line emitting ones. So that was largely just seeing which of these galaxies shows L is greater than 0. But even further than that, we wanted to do some selections for the quality of the photometric flux data, as well as the quality of the chi-squared minimization. So those are some of the selections that we made here, as well as we preferentially selected the more higher excess flux emission, so higher values of L, just to be kind of working with galaxies that had sufficient emission for us to kind of find interesting things when we were trying to create the maps and compare to the rest UV continuum emission. And then the second thing was making sure that we were selecting galaxies in that redshift range of 4 to 5 that we were looking for. So Katie gave a great description of the EASY program to estimate photometric redshifts. So I also use EASY, and the photometric redshifts, it estimates for all the galaxies in the JADES images to make sure that I was selecting ones with photometric redshifts between 4 and 5. But furthermore, especially the galaxies that were more morphologically complex, so they had a lot of components, we wanted to make sure that we were selecting galaxies that seem like all of the components in the system are of the same redshift. So this is definitely with the spatial resolution capabilities that JWST has. It's a good problem to have, but we wanted to make sure that we were certainly selecting systems where all the components seem to have the same redshift. So it was a pretty simple, just a photometric Lyman break dropout Also, Katie gave some good insights into how that Lyman break dropout method works. But using HST images, and you can see, for example, here's one of the galaxies in the sample, and all of the components are disappearing together, so that's a good thing. So ultimately, after applying all of these selections and cuts, we have 75 galaxies that we identified as H-alpha line emitters in the good south field. And the first thing I'll talk about for this sample is the variety in the morphologies. So this is really fantastic. It's just really beautiful to see how complicated the morphologies are, and very exciting to be able to probe this with continuing future work. But for example, I have images of 4 different types of morphologies that I classified for my sample. So I just went through all 75 galaxies, visually inspected them, and classified them based on at least preliminary features, such as compact galaxies, that even though they might seem like a simple morphology here, it's actually not so trivial that maybe when we do kind of some more quantitative work with trying to measure star formation rates or something like that, pixel by pixel, we might find some more interesting things than just some compact point source looking morphology. So even though these are simpler, they're not necessarily super trivial morphologies. And then another category I made was bimodal, where I could see kind of 2 really clear-cut components that seem to be part of the same system. That's as opposed to extended, which the other component isn't so clear-cut, like it seems like another well-structured component, but more so kind of like I saw almost like tails or just remnants of interactions that these galaxies were going through to kind of create these interesting morphological features. And then, of course, we have the super multi-component galaxies that are just super exciting. So some other properties of this H-alpha line emitting sample include distributions of the redshift of the galaxies, as well as that excess flux in the 3.56 micron filter. So that's that L parameter. And I also looked at these distributions based on the different morphological classifications to see if there was some interesting connection there. So the thing I'll note about the redshift distribution, seems like all the morphologies are pretty, are kind of distributed in relatively the same way, but at least we can see that if you remember from that figure with the green filter set adjacent with the 2 others and that black circle that was like the window we were looking for, that these redshifts are corresponding to exactly that window. So that's a good sign with how the technique was able to work. But then for the distribution of that L parameter, we see that the compact morphologies kind of seem more exclusively set towards smaller excess fluxes in the 3.56 micron filter. So that's something interesting to note about that distribution. All right, so the second phase of the project was actually creating the maps. And this was a really great challenge to work through in the project. I had a lot of fun learning about all of the different techniques involved, especially just learning so much about the point spread function of these, of JWST. But to motivate the techniques I used, I'll first set out the ultimate goal that we're going for, which is to compare pixel scale line emission maps of the rest UV continuum emission, which for redshift 4 to 5 we can set to be in that 1.15 micron filter, and compare that to maps of the H-alpha excess emission, which, like we said, we're trying to map pretty much the 3.56 micron image. And these 2 are the point spread functions for the 1.15 and 3.56 micron filters. And the point spread function basically sets the spread of how objects are imaged in observations, and the point spread function is determined by pretty much the optical properties of the telescope and the instrument. So it's really important then that we're able to kind of maintain the scales of each of these point spread functions kind of with the image they had, but also be able to compare apples to apples between a map, between images in either of these 2 filters. So what we have to do is basically take this point spread function and smooth it to the level of this one so that we can compare those apples to apples instead of apples to oranges. So that's the process of PSF matching, and in order to do that, we have to understand the point spread function. So there's a program called WebPSF that simulates point spread functions for JWST instruments. So that was the baseline that I took for the point spread functions to use in my PSF matching. And actually there was a component of my project that I don't talk about, but if anyone has any questions, I'm happy to discuss that later, that I actually worked on trying to validate that the WebPSF point spread functions do a good job of modeling the PSFs. So we can take the WebPSF and kind of put it through the same data processing pipelines that each of the observations in the JADES observational program went through. So that's things like mosaicing and the other data processing techniques. And that just really allows us to have a point spread function that's representative of the actual images that we're trying to use it for. So we can call this the model PSF or MPSF. And I have a picture of that here of what that looks like. But you notice here there's a lot of structure, complicated structure in the outer regions that's actually not so important for us to be able to use in making sure that we can PSF match images of 1.15 to the 3.56 scale. So what we did to kind of get rid of that extra complexity was just simplify it and model it with a Gaussian. So we really care about that central region in the PSF. And this is actually a Fourier transform of the PSF. Which is used in the convolutions, but this just really shows kind of that radial symmetry and the simplicity of the outer regions of the PSF. And like I said, the central region was really what we cared most about modeling properly. And so here is a kind of one-dimensional slice of, this is no longer the Gaussian Fourier transform, but just the regular PSF in image space. And we can see that the centers are corresponding well. So that's good. We can go ahead and use this Gaussian PSF model to be able to convolve our images. So if we start with the raw images up here, the image in 3.35, 3.56 and 4.1 microns. This is that flux continuum. And we care about that H alpha line excess, right? So we want to isolate the H alpha line emission. So essentially what's done is we just go ahead and subtract the 3.35 and 4.1 micron images from this 3.56 micron image. And this here is then the resulting H alpha line emission map. But then if we look at the rest UV continuum emission map up here in the 1.15 micron filter, we can see the effect of that PSF being a lot sharper for the 1.15 micron filter. So we can see here that the same kind of components and morphologies just look a lot more sharper than these other images. So this is truly the image that we care most about being able to smooth to the level of this Gaussian model of the PSF for the 3.56 filter. And so once we apply that convolution and smooth the PSF of this to the level of the Gaussian model, now we have a really nice image of the rest UV continuum emission that we can actually compare because the scales are comparable now between the two images. So what I did from the sample of 75 galaxies was I just chose 5 which were pretty interesting to me. There wasn't really too much more rigor than that. One thing I did try to do is try to select some varying morphologies just to be able to sample some different features. But these are the 5 galaxies that I chose in my sample, and these are just composite color images. So they're not the convolved images or the line emission maps or anything. But yeah, so we can see we have some combination of like compact, we have some multi-component things going on. This one I found interesting because it seems like it kind of has a little tail feature that would be interesting to look at in the emission line maps. So what I'll do now for the rest of the talk is just kind of walk through the resulting H alpha and rest UV line emission maps for these 5 galaxies. Kind of talk about some preliminary thoughts that we can make to study further. The true scope of the thesis was to be able to make the H alpha and rest UV line emission maps in the first place. So these next few things and kind of ideas we can have for what might be going on in the galaxies is a lot more work left for future studies to do some more quantitative measurements with. But nonetheless, they're definitely fantastic to look at. So for example, this is that first galaxy that I was interested in that kind of tail feature. So it's interesting that it shows up in this rest UV emission map compared to the H alpha where it doesn't. And I'll actually take a second here to just reiterate the comparison between H-alpha and rest UV emission. So remember that the H-alpha line emission is probing a lot younger star formation, whereas the rest UV continuum emission is more susceptible to being affected by dust and is also some older stellar populations. So then this difference image here is literally just subtracting with appropriate kind of scaling factors this H-alpha map from the rest UV map, and then we can see exactly kind of what components are showing the most emission in either rest UV or H-alpha. So in the next few slides too, where we see that means that there was more rest UV emission than H-alpha. And then if you see a really bright yellow, that's more H-alpha line emission there. And I'll note quickly too that these two plots at least are scaled with the same color bars, so we can also kind of see those comparisons there. But yeah, this one has a really interesting tail feature in the rest UV. Maybe that's suggesting some sort of interaction with another galaxy throughout its lifetime that kind of left it with like a tidal tail feature that might appear to be more dusty or older star-forming populations or something like that. So this was for sure an interesting galaxy to look at. Then I think this one's my favorite out of the whole sample just because it's so amazing. And we can see just so wonderfully spatially resolved components of star formation in this galaxy. And it's really interesting how some of them compared to others are really emitting more in the rest UV compared to H-alpha. So yeah, this one's going to be a fantastic one to follow up with more specific, I was going to say more specific star formation rate measurements, but I don't mean necessarily specific star formation rate. More particular, I guess, star formation rate measurements of these components. This would be a really interesting one to follow up as well, to kind of look if we can probe some of the kinematics of these components and the dynamics of the galaxy, see how they're kind of interacting with each other or where they fall in the physical processes of this galaxy creating this type of morphology. But yeah, this one's very interesting. Then this one here is also quite interesting. These are really faint in this whole normalized emission line map, but there's three components that are down here in this image, as well as the much brighter components up there. And this is still kind of an ambiguous one to me because when I did that Lyman break dropout technique to check that the components in the HST images were all dropping out in the same filter, and also when checking the photometric redshifts for these various components of the system, they all appear to be part of the same, at least within the same redshift. So it's still a little ambiguous to me whether these are possibly part of the same system or just different systems that coincidentally are kind of nearby. So that's something definitely to probe further with, like I've been mentioning, those more quantitative measurements. But even yet in this component up here, really great kind of separation of the components with which ones are H-alpha or rest UV emitting. And then here we have another really interesting one where some of the components more than others, especially the outer two here, are very varied in how, whether they're emitting in rest UV or H-alpha primarily. And so these are also kind of difficult to pick apart, whether these are kind of dust effects or just older star-forming populations that are kind of creating these discrepancies in the H-alpha versus the rest UV. So that's something that we'll be continuing to probe as we look at these, look at the sample of galaxies more carefully. And finally, this is one of the compact morphologies. And like I said, they might not seem too interesting to begin with, but this will be another one to follow up with pixel by pixel measurements of those star formation rates and other types of probes to understand the properties of the star formation. But at least this one primarily is an H-alpha line emitter compared to rest UV. So really young star-forming really active star-forming galaxy there. So I've been mentioning kind of with the walking through those 5 different galaxies, some of the future work that we'd really like to do to be able to probe this sample further, because in the literature and just what's been able to be accessible previously, this range in redshift between 4 and 5 is just kind of really a gap in the knowledge of what we understand about how star formation is evolving over time. And so it's really great to be able to begin filling in that gap with these JWST images. So the first thing I've been mentioning quite a bit is actually making star formation rate measurements pixel by pixel, also to be able to get a sense of the dust attenuation effects, so exactly how much the dust content of these star forming components is affecting how we're seeing them in these different line emission maps. And another thing that Maya kind of mentioned in her library, creating the library of SEDs, is that it's not so clear whether the assumptions that are involved in making star formation rate measurements, largely assumptions that depend on the form of the SED, a lot of the work that Maya is doing in setting up those templates, it's not so clear that what we know about those assumptions for lower redshifts can be translated to higher redshifts. So that's something that will kind of take some more nuance to explore when we begin making these more quantitative measurements. Another aspect that's really interesting to continue probing is the morphologies. It can be really interesting to do some more population type studies of the morphologies. So perhaps comparing the variety of morphologies in the 75 galaxy line H-alpha line emitting sample to the variety of morphology seen in some other like control group of galaxies that's not H-alpha line emitting or not at redshift between redshift 4 and 5. And also trying to probe the star formation for different methods of classifying the morphologies. So I just did them visually, like I explained, based on what features I was seeing in the images, but they can also different morphologies can begin to be connected to physical mechanisms that create those morphologies. So that's another interesting route that this work can take to kind of continue exploring the connections between those morphologies and star formation. And finally, this work has a really big potential to be able to contribute a lot more insight into dust and the role of dust in affecting different star formation tracers for galaxies at these redshifts. And yeah, just really understanding the dust content of these galaxies, especially by looking more into the UV continuum and perhaps using other filters to be able to see what discrepancies there might be between the REST UV emission maps we made for the 1.15 micron filter compared to some of the other REST UV filters that JWST has access to for these galaxies. So I think I'll end there, and of course, thank you so much to my advisors, Daniel and Ben, and also Maya and Katie. It's been such an enriching experience, kind of this endeavor of the senior thesis and working with JWST data. It's also been so great to be part of this class cohort. I think we've gone through a few long years together, so it's great to see it all come full circle with these senior theses. And yeah, I'm really excited about where this work is heading. We've laid out the foundational work, and now there's a lot of measurements to do. So. Thank you very much, and I'm happy to take any questions.
Had of the like excess different between the filters.
Yes.
Yeah. So I think the one that stood out to me the most was the lack of compact galaxies at the higher excess things. Do you have any ideas for like an explanation behind that?
That's a great question. One I've been asking myself, because of course we note that the compact galaxies appear to be lower in excess. Something that I think I want to look into a little more is exactly also the selection of whether these excess line emissions are also kind of corresponding to the overall flux of those objects as well. So something that we did want to look at was the ratio between this excess 3.56 micron H-alpha line emission, the ratio of this to that amplitude A of the power law continuum to see what relations were there. Yeah, that was, yeah, I didn't quite get to do that in time for the presentation because there were some nuances there with the normalization of how to normalize these two quantities to compare them. But that's something that I think definitely that would be more insightful to your question to explore that.
Other questions?
Also, for some of these components, it looks like they may be like very separate. Is there a way to get a sense for whether they're interacting or maybe we're just by chance seeing in the same place and they may be different distances?
Yeah, so definitely kind of the more three-dimensional distances I think we were able to address that with looking at the redshifts of each of the components, especially with the photometric Lyman break dropout, looking at that with the HST filters to get a sense of whether these components really were kind of in the three-dimensional space nearby, which at least based on my sense, it seems that they are. But otherwise, the physical, let me actually see if I think some of these. Okay, so this is a good example, I think. So for galaxies at this redshift, these physical scales of arc seconds are corresponding to about like 6.5 kiloparsecs per arc second. So that was a question initially when I made these maps. I was like, whoa, are these like actually one galaxy or different galaxies? So it's definitely really impressive that we're able to spatially resolve and that we have this question to begin with. But so for example, I have a scale bar here really nicely, 1.5 arc seconds. That seems to be maybe roughly like about the spatial spread of that galaxy there with all those different components, and if it's like 6.5-ish kiloparsecs per arc second. So that's still very much within the regime of being like one system and one galaxy. Yeah, that's something interesting to probe to, exactly how these scales, how we can compare them to other work of galaxies at this redshift or galaxies at kind of adjacent redshifts to see if those scales are changing over time as well, if we can probe that further with this. But yeah, that's a great question.
Very good. Okay, let's thank Natalia one more time. And while our last speaker is setting up, let me remind you the cookies in the back will not eat themselves. So please dig in.
Shot. Okay. Let's see if I can do this. Okay. Oh, thank you. Shout out to James Webb. Turns out it's pretty good. That's what people are saying. Okay.
All right. So here we go. Our last speaker of the day is Chris Worth, and as you can see from the title, he's going to be talking about a transit search that he developed using test data to search for ultra-short period planets. And Chris actually has some experience looking for young stars and young planets. He started working with our group a couple years ago after his freshman year and throughout his sophomore year working on a project to identify young stars, which led to a couple papers, one where he led the characterization of a young planetary system, and then another where he contributed in a key way to a discovery of another planetary system. He took a little break and explored some other areas of astrophysics and expanded his horizons, and came back to us for his senior thesis. And it's been a real pleasure working with Chris. I think this is a really important, some really important work that helps us understand some open questions in the field of exoplanets relating to how stars form and how they evolve. And I'm sure Chris will tell you more about that. I think it's not a spoiler now to say that next year you'll be spending your time in grad school at the University of Chicago. So take it away, Chris.
All right. Thanks so much, Sam. Everyone, thanks so much for being here. An amazing job to all my classmates who have done such incredible work that I really enjoyed getting to hear about. So yeah, as Sam said, I've spent the past year, advised by him, exploring the field of young ultra-short period exoplanets and developing a specialized search for these targets. So since the first exoplanet around a sun-like star was discovered in 1995, there have been over 5,600 confirmed exoplanets. With this many discoveries, many of the open questions in the still young field of exoplanet research are centered on the details of how exactly planets form and evolve. So there are many steps in the planet formation process that are difficult to explain, that we need to fill in our knowledge about, as well as many different proposed mechanisms for how the observed populations of planets that we see ended up that way. One more specific questions of particular interest to the question to the area of young ultra-short period planets is that of atmospheric mass loss. Which planets lose their atmospheres? How do they do so? Why do they do so? And so important questions like these motivate the work I'm presenting today, which will hopefully bring us one step closer to improving our full picture of the birth and development of planets in general. So, super brief, simplified overview of how planets form and evolve is that they start out in a circumstellar disk, a byproduct of the star formation process that's required by conservation of angular momentum. Nice little sketch is on the left. Dust and gas in this disk coalesce into planets, and this process needs to happen in the first tens of millions of years of the star's lifetime before the disk is evaporated. After the planets are formed, they interact gravitationally with one another. Right? Just because the planets have been fully formed does not mean that the system's architecture is completely set, because there's still dynamical scattering, migration, all these sorts of things. A process, kind of generally called dynamical evolution, which can continue to shape the architecture of a planetary system for hundreds of millions of years. So these timescales are a bit different, and it's also over this a bit longer timescale that we might expect atmospheric mass loss to be taking place. So some methods that have been used previously and are being used to explore these questions of formation and evolution are first, we can kind of go to the shorter end of the timescales and look at disks directly, either through observations or laboratory experiments, this allows us to tackle questions of formation. But often, these techniques are a little too early to get at kind of a lot of the effects that really end up shaping planet populations. Alternatively, we can look at the 5,600 exoplanets we know and say how do we have these planets? How do they get here in the first place? We can kind of extrapolate backwards into the processes that must have shaped these. But this is too late. They're old. We can't catch them in the act. In the same way that if we could look at planets that are tens or hundreds of millions of years old, then we could be like, oh, this is actively losing its atmosphere. Oh, this is actively moving inwards. Stuff like that allows us to really dive into these questions. So this tens to hundreds of millions of years region is where a lot of the action is in migration and mass loss. And so we could study this more directly by finding and characterizing young and adolescent planets. So to go for this goal, I use NASA's TESS mission, which stands for the Transiting Exoplanet Survey Satellite. This is a space telescope that uses the transit method to detect planets. And this is the most prolific method we've used. 4,000 out of 5,600 is a very high fraction. And brief overview of how this works. If the orbits of the stellar system of the planetary system are angled just right towards Earth, the planets will move in front of the star from our view, blocking some of the light, and this causes a characteristic dip in the plot of the brightness of the star over time, which we refer to as the light curve of the star. And so this signal will repeat at the orbital period of the planet. How deep it is corresponds to how big the planet is. The depth is the square of the ratio of the planet's radius to the star's radius. So it's easiest to find big planets around little stars because they block a big percentage of the light. And it also reveals, it tells us we're looking at the disk edge on, the system edge on, and can do a lot more specific stuff like eccentricity as well. So we get a lot of essential parameters from just this signal, just little dips in the light curve. And so since all we need to do is it's still hard. We can take tons of, if we just look at the light curve and say, oh, is this star dipping in brightness? This has been a very prolific method and allowed us to get a lot of new exoplanets. And TESS specifically has collected photometric data of nearly the entire sky. That was its goal. It's doing it very well. Readily available, open source, to search for transits. You can go download it and look at it now if you want. Okay, the first planets discovered, as I said, using this method, were a population known as hot Jupiters. Does my mouse work here? Oh yeah, hot Jupiters, right here. these are the biggest planets at pretty short periods. So you get lots of transits, and they're very deep. So these were the first ones to be discovered by ground-based surveys. And then once we had dedicated missions, and then they're here on this plot, and this plot is showing the orbital period in days against the size of the planet and Earth radii. And this is specifically a sample called the California Kepler survey, which is kind of a uniform sample of a bunch of known exoplanets. Yeah, so the hot Jupiters are up here, but obviously there's all this stuff down here. So how do we get that? Well, this is through these dedicated missions. Specifically going to space allowed us to do a lot and kind of push the threshold down to longer period planets. Kepler, for example, the predecessor to TESS, just stared in one section of the sky for multiple years and was able to get really long period planets by seeing these repeated dips over these long periods. And it's also higher precision has allowed us to push to smaller radii as well. So we're able to fill out much of this parameter space. And as we discover more and more planets, two main populations of small planets emerge. Super Earths at about 1 to 2 Earth radii, and mini Neptunes at about 2 to 4 Earth radii here. So these are the super Earths around here. These are the mini Neptunes. And in fact, it's been shown that there's actually a gap between these populations in the occurrence rate, or the fraction, the number of planets per star, at about 1.7, 1.8 Earth radii. There's actually, they're very much two separate populations. That was a recent discovery. That's very key, and the specifics of this gap are a very key constraint of something weird. Very key constraint on our models of exoplanet atmospheres, because it's believed that this gap is kind of driven by atmospheric mass loss itself. So the population that I focus on in this work, the ultra short period planets, are these ones, which are defined to have a period less than 1 day, the ones highlighted in yellow. And so these are population of planets. Here you can see that they're mostly have radii smaller than 2 Earth radii. So they're not likely to have something like extended hydrogen or helium envelopes like we might see in a lot of the mini Neptunes. This is likely related to their extreme temperature, since their periods are so short. They go around their star every day or less. That means they're super highly irradiated, tidally locked, so permanent day side, night side. So they're just getting blasted by radiation. Likely can't hold on to extended envelopes. And the sparse region of parameter space above most of these USP planets, which extends out to almost 3-day period planets here, is known as the hot Neptune desert, because they would be hot and they would be Neptune-sized if they were there. But there's nothing, so there's desert. There's a couple things which are very interesting targets. But some planets that might have started initially in this region might have lost their atmospheres and thus moved downwards on the diagram to their observed locations. So the discovery, study of young planets is a key step to understanding processes that could have shaped these different populations. For example, this Rogers and Owen plot here represents a simulation in which they track the size distribution of planets across time using only a photo evaporation model to explore one possible theory of atmospheric mass loss. So even by 100 million years, we're able to see kind of bimodality in this distribution, which eventually in their simulation leads to a reproduction of the observed radius gap on the right. So exploring planets at these ages actively undergoing this process could inform more directly our understanding of how these exactly would work. So with reference to USP planets specifically, observing these targets across different ages can allow us to differentiate between different ways that these objects could have arrived at their observed locations. Why do we think they have to arrive there? Well, they're so hot. Some of them are so close to their star that the distance between the planet and the star is only 8 times the radius of the star. So these guys, it's even above the sublimation temperature of dust. So you can't even get dust around to coalesce into a planet. So they must have formed farther out and somehow moved in. How did they do that? Well, there are a lot of theories. One proposed mechanism has the planet kind of drifting through the disk while the disk is still around, but that requires the disk to be still around. So that's got to happen in the first tens of millions of years. So if that's the case, that's a fast method. Others are more dynamical in nature. They involve scattering with other planets after the disk is already dissipated, scattering up into maybe inclined and eccentric orbits that gradually circularize through tidal forces. That takes a lot longer, doesn't require the presence of a disk. So as an super extreme example, if we were to look at a bunch of young planets, young ultra-short period planets, and see that there's just as many young ones as there are old ones, then we would say, like very young ones, then we would say, oh, well, they must have formed quickly. So then the disk migration scenario would be favored. If we were to see nothing at young ages, then the slower method, like a slower method such as these gravitational methods, might be favored instead. So clearly, discovering lots of young planets would be a huge benefit to our understanding. But actually observing these important young systems is made difficult by, as Serena talked about so much, well, she didn't do young stars, but activity sucks. So young stars are extra active. They have more star spots. They rotate faster, which creates confounding photometric signals as spots appear to move across the stellar disk, as in this animation where the bottom curve tracks the brightness of the star as these simulated spots move around. So that, if you want to look for little dips in this, the amplitudes of this effect are multiple orders of magnitude higher than transit depths. So if you want to look for little dips in this, that's a lot harder. And this also can affect mass measurements. And to measure a planet's mass, we generally use the Doppler signal of the star's rotation around its shared center of mass with the planet. But these star spots introduce variation in the signal as well. So so this is difficult. But if we're looking at USPs specifically, this actually is not as hard. Because, first of all, closer in planets have a stronger gravitational force on the star, so they induce a higher amplitude radial velocity signal. Second, the difference in timescales between stellar rotation and the planet period allows for mass measurements using careful observation scheduling, where if we look at a portion of, we're able to get enough of the period of the planet's orbit in just one night of observations that the stellar rotation doesn't change too much. Similarly, very short transit durations of USPs, if we're looking for transits, allow the planet signal to be separated from the stars. As an example here, this is a star with a 2-day rotation period, and I put in fake transits of a planet with a 0.6-day orbital period, shown in blue. And so the shaded regions here represent the transit duration, which is much shorter than the timescale of variability for this star. And if we zoom in on one of the transits, the variability is approximately smooth in the region around it and can probably be effectively modeled away, allowing the transit to be detected. So overall, we see that ultra-short period planets are interesting to study for their own sake, since they're an extreme population with interesting formation scenarios. But they're also our best chance to study young planets in the midst of stellar activity. Even though they're an extreme population, the lessons we can learn from studying them are still applicable to the broader population of planets, since for one, they represent important calibration cases for our models of photoevaporation due to their very high stellar radiation. The USP planets without atmospheres are also representative of the cores of cooler planets and are therefore amenable, and since they're so hot, they're amenable to studies not possible for cooler planets, such as emission spectroscopy, that can help characterize the rocky surface. The ones with atmospheres, of course, are also essential to our understanding of atmospheric escape as well. So I set out to search for USP planets around young stars using a pipeline I created specifically for this purpose. But if I want to search for young planets, I need to look around young stars. So I need to get some young stars to search around. I compiled a sample from the literature, specifically these 3 papers there, of stars that were identified as young. Happy to talk about how they were identified by these papers in more detail later if people have questions. But essentially they were placed in kinematic associations, moving together with other young stars that kind of were characterized all as a group together. Hey, all these guys are young. And there were a total of about 35,000 young stars in the sample. I used a threshold of about 200 million years to call a star young, presented in these papers, but only 6,610 of them had data at a 2-minute cadence with TESS. And the reason I cared specifically about this cadence for the data is that the short transit durations mean that if we use the full frame images from TESS, at 10 or 30-minute cadence, these would likely smear out these transits over too much time. You wouldn't get the resolution. You wouldn't be able to resolve the planet going in and out of transit, and you'd lose a lot of information. And it would barely even look like transit. So yeah, but as TESS moves in the second extended mission to 200-second cadence for every star it observes, the sample can be broadly extended, which would be really exciting. So the sample of these about 6,000 stars are shown in somewhat of an HR diagram here, plotting stellar effective temperature against the radius. And so these are colored by the age given in the literature. Bluer stars, the bluer points represent younger stars than the yellower points. They do kind of follow along somewhat of a main sequence, though we do see some inflated stars at the youngest ages, especially at lower temperatures, which is expected. But there are definitely a decent amount of large radius stars, which would decrease our sensitivity to transits around them because of the reduced depth of transits around larger stars. So the first step in actually searching for USP planets around young stars is accounting for the rotational signal. So to leverage the main advantage that we have looking for USPs, which is the difference in timescale between the transit duration and the rotation period, I needed to find the sweet spot between overfitting the rotational signal, as in the top row, where if you're not fit to the actual rotation, if you divide out your model, then it doesn't go away, and you haven't even accomplished anything. To overfitting the rotational signal, where our model eats away the transit, and then when we get rid of the model, there's no more transit, or it's completely unrecognizable. So to model the rotational signal, I used a spline fit, which is a set of polynomials smoothly stitched together at some characteristic spacing called the breakpoint spacing. And so the more fine the breakpoint spacing, the higher chance of overfitting, like in the bottom, and the coarser the breakpoint spacing, the higher chance of underfitting, like in the top. So I experimented with these breakpoint spacings. Also happy to go into more detail on the experiments later. But I found that underfitting happens. So you underfit when the spacing is greater, farther apart than about 1/6 of the rotation period of the star, and you overfit when the breakpoint spacing is finer than about 3 times the transit duration. So calculating the longest possible transit duration, since we would and specifically for circular planets, because we'd expect these to be circularized since they're so close to their star. For a USP planet around a sun-like star, this gives us about 0.1 days as our spacing, 3 times which is 0.3 days. So we chose 0.3 days as an intermediate breakpoint space because where ideally the rotational signal is detrended and the transits remain as so nicely happens in well, this is fake data, so I made it look very, very nice. But ideally, this is what happens, and these are the resulting light curves that we search for transits in. But sometimes, right, if the star is rotating really fast, these timescales can overlap, and there is no sweet spot anymore. And this specifically happens if the rotation period is 1 or 2 days. Like looking at the sample that we have, that's only about 15% of the sample, and we don't expect the sensitivity to be completely removed. That's something we need to revisit in more depth, absolutely exactly how that happens. But we don't expect that to be removed, and it's only 15% of our sample, so that's not the end of the world. So this is a good starting threshold. So after this detrending takes place, hopefully our light curves look just like that. And then I specifically use the transit least squares algorithm to search for transits, which looks over a grid of possible periods, transit depths, stellar parameters to find the best fit model. And I restricted that specifically to periods less than 1 day, because that's what a USP planet is. So to test the sensitivity of the pipeline, I injected every light curve in the sample with the synthetic transit drawn from a uniform distribution in planetary radius and period. I then ran the pipeline on these artificial light curves with transit signals injected, and observed whether the original parameters, I observed whether I got the same thing back that I put in. If there's a planet there, do I get it right? And as expected, the pipeline was more sensitive to planets of larger radii because, as shown in the left-hand plot, showing the recovery rate, the fraction of correctly recovered planets in different radius bins. So that's increasing, and then similarly for around larger stars, we're less sensitive because of the reduced depth of transit as well. That's what's shown in the right-hand plot. So we would expect most planets at these periods to be less than 2 Earth radii, as we've seen from the more evolved sample. And we're particularly interested in observing them around sun-like or smaller stars because of the ease of characterization. And so for planets like this, less than 2 Earth radii around stars smaller than the sun, we have a 66% recovery rate, which isn't bad. However, these are uniform. These injected parameters are uniform across period and planetary radius. This is not what we would expect to be the case in real life, because we expect the actual occurrence rate of planets to vary as a function of radius and period, as well as our sensitivity to these planets, as we see here. So if the number of planets we actually discover in the sample can be accurately determined, then we can actually use this to go backwards statistically and say, we found this many, this is how many we're sensitive to, here's how many there must actually be. And this would allow us to determine the occurrence rate of young USPs, which would be a very valuable analysis. So with confidence that our pipeline can correctly identify our targets of interest, I applied it to the test light curves with no injections or anything of the sample. So the algorithm triggered with signal to noise greater than 6 on about 2,000 signals, which I combed through by hand, looking for metrics that might reveal various false positive scenarios, which I'm happy to come back to if people are curious later. I'm just excited to get to results here. I'm running low on time, and then I qualitatively rank candidates based on their transit shape and some more quantitative methods as well. So overall, I identified 51 planet candidates, which are plotted over the HR diagram of the sample on the left in blue, where the darker a point is, the higher priority it was ranked. And our most promising candidate is shown in red. As we might expect, higher quality candidates around smaller stars. On the right, the candidates shown over this California, in period radius space, over this California Kepler survey that we used before. And of course, and it's just converted to a contour plot. Of course, they're purposefully located at short periods. That's specifically where we looked. But they are also mostly larger than the distribution of the CKS ultra-short period planets. Many of these are likely false positives, but young planets have been shown to have larger sizes on average. So this might actually be related to the atmospheric mass loss. So these larger radii might not be surprising. And then I'd like to finish talking about the results by highlighting 2 very different promising candidates. Number 1 is not a USP planet at all. This is actually very long period, and it's still shorter than Earth probably, but it's long period in terms of our known populations, because there's only a single transit in a whole sector of test data, which lasts about a month. So this is not what we're looking for at all, but it popped out of this survey. And so we only have one transit, so we don't know really what the period is. But since the transit duration is related to the period, we infer that it's somewhere on the order of a month-long period. Its radius is about 4 to 5 Earth radii based on the depth of the single transit that we have, and the star has been identified to be a member of a young moving group that's about 11 million years old. So that's very young, and this would be really exciting because this would be one of the longest period young planets ever discovered. It would, and it's particularly large as well. So we could really explore the question of, how do young planets lose their atmospheres at long periods, which isn't the question I was trying to answer, but this would be awesome to check out anyway. And still a very important question, of course, maybe even more related to Earth-like planets. Okay, this is more like what we were looking for. This is a candidate, an ultra-short period candidate, period of about 0.74 days, radius just less than 2 Earth radii. And it's a star, around a star that's estimated about 200 million years old. The error bars on that are very large, but it's probably pretty young. And this is particularly interesting because it matches really well with a ultra-short period planet that has been researched extensively, 55 Cancri E. It's the same. It's just about the same size, just about the same period. The star is very similar. They're both sun-like stars, except this one is much younger. so there's a possibility for a comparative study of, here's this planet we know really well, here's this younger version of it, which would be really, really interesting, especially because this is around a very bright star, K magnitude 7.3. So it's very good for potentially following up. And it's hot, so it could be measured with JWST as well, which would be really, really awesome. Okay, so improvements, possible future work. Of course, let's look at these candidates more. These are super exciting. Also, not just these two, but all 51. If we were able to there's no way they're all real. So let's eliminate a lot of these false positives that we expect to come from our sample. And if we're able to do that, as I mentioned before, we can kind of go backwards and say how many of these types of planets actually exist out there. And that could be a huge, really important benchmark for differentiating between different formation scenarios of these types of planets and planets in general. Of course, the pipeline needs to be improved always. We could directly account for effects from TESS, the spacecraft itself, and we could also explore what exactly is going on with the fastest rotating stars. How sensitive are we there? What can we do to improve that sensitivity? And then, the sky's the limit for this, pun intended, because TESS is moving to 200-second images, full-frame images, which can open up any star we want to be kind of examined by this method. So yeah, that's what I have. Just want to thank so much Sam for being an incredible advisor, showing me this awesome project, to Dave as well for getting me into exoplanets, showing me Spectra in his office, and Giorgio as well for helping me find this sample and really teaching me to be an astronomer in the first place. So yeah, and to my incredible classmates, family and friends. So yeah, thanks.
We can take one or two questions if there are questions. Yeah.
I was kind of curious with the, is it break spacing parameter?
Breakpoint spacing.
Breakpoint spacing parameter. Was that fitted by hand or was that fitted by like a neural network or something?
Yeah, so I kind of chose specifically, I think, let's see, I have a backup slide showing this. So I specifically chose this by hand. I chose 0.3 days because it's kind of intermediate here. It's kind of intermediate between the overfitting and underfitting. So here, if you look at the breakpoint spacing versus transit duration, this is the results from the experiment where we kind of see that the overfitting, where the depth of transit really starts to decrease when this spacing becomes finer than 3 times the transit duration. And then so for the transit duration, the longest possible transit duration of a USP planet around a sun-like star is about 0.1 days, so 3 times that is 0.3 days. So I just said, 3.3 days, because you're gonna be able to not underfit if the timescales don't overlap. You're not gonna be worried about underfitting more if you go as fine as possible. So 0.3 days, but that's definitely a future thing to do is maybe more systematically relate this spacing to maybe the rotation period.
Last question, because we're pretty low on time. Yeah.
Yeah, so going back to like your overall sample, and specifically I think you plotted it on an HR diagram,
Mm-hmm.
I was really interested to see how few stars you had around, or few planets you had around around M dwarfs specifically.
Mm-hmm.
Yeah. Is there a reason for that? Is it just that you started out with less, or is there another?
Yeah, so definitely started out with less. Then also the important aspect that I'm glad you gave me the opportunity to bring up is that these 2-minute cadence observations they're not a uniform sample. Basically, they were selected through proposals for like, hey, let's look at this star with higher cadence. So this sample is rife with selection effects. Specifically, there aren't that many M dwarfs. They're also fainter in general, so you're going to have harder time observing around them. So yes, obviously it would be great to get to check those out, and our opportunities to do so will be much more widely available with the move to 200-second cadence in the second extended mission.
All right, I think we can thank not only Chris, but all of the senior thesis concentrators.